जी हेलो, माइक टेस्टिंग 1 2 3। हेलो हेलो, माइक टेस्टिंग। आपको आवाज़ आ रही है? हेलो, डिस्टॉर्शन तो नहीं है? चेक कीजिएगा प्लीज़। हेलो। बोलिएगा।
Hello, mic check. Hello, 1 2 3. Hello, mic check. Hello. Hello, mic check. 1 2 3. बोल दो यार। पीछे हैमिंग वॉइस।
बड़ी क्लियर नहीं है।
Assalamu alaikum, ladies and gentlemen. I am honored to welcome you all to the third session of 7th International Conference on Energy Conservation and Efficiency 2024. We appreciate your interest and thank you for attending our conference. Your presence here enriches our discussions and contribute to success to our events. I am Alina Raza and I am privileged to co-chair the session with session manager Mr. Danish Naseem and session chair Dr. Kashif Imran. Dr. Kashif Imran received the BSc and MSc degree in electrical engineering from UET Lahore in 2006 and 2008, and the PhD degree in electrical engineering from the University of Strathclyde in 2015. He received the Commonwealth Scholarship for his PhD research. He has worked at the Transmission and Distribution Division, Siemens, and the Power Distribution Design Section, NESPAC, from 2006 to 2007. He was a faculty member at the University of Engineering and Technology and ComSat Lahore. He was the inaugural head of the Department of Electrical Engineering at the US-Pakistan Centers for Advanced Studies in Energy, NUST, Islamabad from 2018 to 2021. He participated in semester-long energy research training at Arizona State University in 2019. He is an associate professor at US-Pakistan Center for Advanced Studies in Energy, NUST. His primary research interests include energy policy, optimization for power systems, electricity markets, operations and planning, as well as smart grid protection. Thank you, Dr. Kashif Imran, for joining us today. In this session, we will have some interesting invited talks on a variety of topics. Our first invited talk is Enhancing Electrical Vehicle Battery Reliability Through AI and Machine Learning Innovations by Dr. Uzaifa Rauf from E-Mobility Research and Development Center, USAID, LUMS. Professor Dr. Uzaifa Rauf, a distinguished academic with a BS and MS in electrical engineering from FAST, UCESE, and LUMS respectively, and earned his PhD degree in electrical engineering from LUMS, specializing in renewable energy systems and applications of AI and ML to enhance battery storage reliability and efficiency. His doctoral research focused on developing advanced ML algorithms for predicting battery degradation aimed at extending the lifespan and ensuring the safety of battery systems in electrical vehicles and renewable energy storage. Dr. Uzaifa Rauf further his expertise as a faculty assistant at the Center for Advanced Life Cycle Engineering in the University of Maryland, College Park, United States, where he worked under with world-renowned professor in the field of reliability, Professor Michael Peck. Currently, Professor Dr. Uzaifa Rauf is at the forefront of the USAID E-Mobility Research and Development Center at LUMS, spearheading projects in electrical vehicle, battery energy storage, and motor testing technologies. His relentless pursuit of sustainability and innovation is evidenced by his extensive portfolio of high-impact publications, emphasizing his contribution to energy data analytics, battery safety, and energy management. Please welcome Professor Dr. Uzaifa Rauf with big round of applause.
Bismillahirrahmanirrahim. Assalamu alaikum. My name is Uzaifa Rauf, and currently this talk is on revolutionizing battery reliability with artificial intelligence and machine learning. I'm currently associated with LUMS Energy Institute at LUMS, Lahore University of Management Sciences, and I'm also associated with Center for Advanced Life Cycle Engineering at the University of Maryland in the United States. So, this is about my education, which they have in brief you about initially about my education in LUMS in fast ICECE, and currently I'm associated with the National E-Mobility R&D Center at LUMS, which is funded by USAID, and I worked with some of the colleagues of Dr. Wakar, Dr. Naveed Rashid. I was his PhD student. I've also worked with Professor Numan Ahmed Zafar, and of course with Dr. Hassan Abbas Khan. So this is my research experience, and it's a long list. I won't go into much detail. And currently, I'm associated with the CALS and NCBC, National E-Mobility R&D Center, and we are currently doing many projects with all these associations. This is just the list of the awards and scholarship which I have got during my studies, during my academic career. But now coming towards the main content of our talk. So Steve Jobs said, if you're really working on something that you really care about, you don't have to be pushed, and the motivation pulls you. So here comes the motivation. As we all know about the electric vehicles and the challenges associated with them. There's a high upfront cost, charging time, range anxiety, and the list goes on. But there is one main problem, which is associated with from where the power of the EVs come from. It comes from its battery energy storage, and there are three main issues associated with the EVs batteries. And so these are the battery degradation. For example, if you have an iPhone, you can see आपकी iPhone की जो battery है या health है वो degrade होती है, and when you go to the market, you actually select that iPhone. अगर आपने use iPhone लेना, you select that iPhone जिसकी health relatively better है. So that is actually called the battery degradation. Then there is a battery swelling, which is obvious. You have seen the battery swelling all around the world. And then there is a more dangerous case, which is battery thermal runaway. So how AI can help in improving the battery reliability? So it's a very using AI in improving the battery reliability. It's definitely a complex process, and it's a very multidisciplinary challenge. So it requires the coordination between the experts in material engineering, material science, electrical engineering, computer science, and other fields. It can AI and ML can help you to develop sustainable batteries, and it can allow the EV consumer to plan for battery replacements or maintenance, which can reduce the downtime and costs. It also optimizes the use of energy in EVs, which can help to extend the battery life and reduce the need for replacements. So the main research application for the AI and machine learning in improving the battery reliability is by developing the predictive models, and which can forecast the battery degradation, can forecast the battery swelling, and estimate the remaining useful life of the battery. This is the overall framework, and through which we can apply AI in the battery reliability. We can have different external parameters like cycling time, voltage range, and temperature, SOC, storage time. And we can use these features, as features to machine learning. And of course, the application outcome would be in the form of the battery degradation modeling and battery swelling. Coming towards the importance of AI in battery reliability. So AI can help in the battery design, and it can have batteries with better energy density, and it can optimize the battery structure to reduce the internal resistance and prevent the formation of dendrites, which is actually the cause of battery degradation as well. Then there comes the battery manufacturing. It can improve the battery quality of the batteries by monitoring the manufacturing process. So the main issues with the batteries actually come from not from the usage, but mainly from their manufacturing process. So there are a lot of batteries. Just my companies, they actually give you the fake batteries. So I always recommend to have a very authentic vendor when you procure the batteries while for your testing, for assembling. And then there is the battery management system. This is the main application of AI in improving the battery reliability. I'm sure you have all heard about the battery management systems, and these AI algorithms and ML algorithms can actually be integrated with those battery management systems, so that can optimize the charging and discharging profiles, and of course it can diagnose any faults in real time and provide timely maintenance or replacement recommendations. And then it can help in the sustainability in developing the sustainable batteries. However, there are challenges and limitations associated with these for using AI in this battery in improving this battery reliability. So first of all, the main thing is the data acquisition. We don't have enough data for battery degradation, battery swelling, or battery thermal runaway. Yeah, the work is being done, and different research groups around the globe are actually working towards collecting this data using different sensors and other technologies. And of course, we need a large amount of data to train the model, because it's a new gold. And data is a new gold in our modern world. So what we are doing at LUMS, we started a pilot project in Lahore and in Multan. It's a swappable battery-based electric vehicles, and if anyone is not aware how the swappable battery works, it's like when your battery is discharged, you just go to the battery refueling station, and they give you the charged batteries, and your depleted batteries are then given to the battery station, and they will charge your batteries. And in this way, you can save the replacement, the charging time, and it hardly takes 4 to 5 minutes to replace the batteries. So this is the project which we started at LUMS. So this is the main framework of our pilot project. It was focused on three-wheelers, and mainly the three-wheelers were procured from Sasgar. And these three-wheelers were electrified using the lithium-ion battery packs. We have the different sensors for the data acquisition, and we are storing that data on the cloud. And we have the 2 battery swapping station in Multan and 2 battery swapping station in Lahore. I'll share more details with you in my next short presentation. So we are getting the data from those rickshaws, and of course, different researchers are actually working on different aspects of this pilot project. So these were the main objectives of this pilot project. I won't go into much detail because the talk is specifically on the battery reliability. So this is the system framework in which we are collecting the data, and we are analyzing it, finding the correlations, and the feature selection is also done. And then there's a predictive model development for the using the machine learning algorithm. We are creating the models, and of course then we are predicting the battery degradation and battery swelling in those batteries. So this is we have some research collaboration done in the University of Maryland, because I've done a PhD which is jointly funded by University of Maryland and LUMS. So one of my co-advisors was the director of this center, and which is one of the leading center in US in the field of reliability. And during our collaboration with CALS, so we actually specifically focused on battery swelling. Of course, there is not much work being done because ये हमें बहुत obvious चीज नजर आती है. But when you go to the literature, you will hardly find any model developments for the swelling, battery swelling, and of course the work is being done for extensively being done for the battery degradation, battery thermal runaway, but there is a mid stage between battery degradation, battery thermal runaway. Battery thermal runaway से पहले ही आपकी battery swelling जब होने लग जाती है, that's what you have to detect while you are predicting or detecting the battery thermal runaway. So there are different aspects of AI and battery reliability research which people can look into, and it's related to the and data-driven modeling that captures the complex relationships between the battery parameters and degradation. Of course, we need the large volumes of battery data, including the voltage, current, temperature, and cycling behavior. And the more we have that data for the batteries related to their reliability, related to the degradation, related to the usage profiles, so we can have more accurate predictions. And of course, there are different methods which have proved to be more useful in the battery reliability, which are assemble methods. And then there are two aspects related with this reliability and AI application in battery reliability. It's the capacity degradation model, in which we have the battery capacity data, and we analyze the battery parameters, and then we can use different algorithms to, and we can integrate with them with the battery management system. And then the same goes with the battery swelling model development, and it can help in the proactive maintenance and reduce the risk of unexpected battery failures. And also it can extend your battery life, and it can sustain your batteries as much as you can. And then the applications of this research, it can help us in the precise SOH estimation techniques. SOH means state of health, which is the battery health. And then there is the optimized battery management strategies. It can enhance the lifespan and improve, of course, the battery safety is the main concern. And also the AI can accelerate the material discovery, the optimized electrolytes which are being used in the EVs, in the batteries, and the different materials. The आए दिन कोई ना कोई आपको technology नजर आ रही है. They are using AI to discover new materials to make more efficient and safe batteries. So this is one of our startup, which is eWare, and in this we are actually using the battery data which we have collected so far, and which we are currently collecting as well. So we are actually using the artificial intelligence, and we are providing some, of course, foreign vendors, predictive maintenance, and the performance benchmarking in comparison with other battery solutions. So what can be the future directions in this field? It can be in the form of diagnostics and prognostics. And of course, currently the work is being done in the battery management system and battery material design, but there's a lot of work to be done in the fault detection and fault diagnosis, which can improve the safety and reliability of the batteries. And the main concern these days is the thermal runaway. I'm sure you have heard the cars catching fire and the trucks catching fire. That's mainly due to the battery thermal runaway. And the earlier we can detect those thermal runaways or the signs or the abnormal behavior of the batteries, so we can make the batteries safer. Then there is a battery second life management. Of course, when the battery health reaches 80%, हम यही समझते हैं कि बैटरी की लाइफ खत्म होगी, but there is another second life in that, and those batteries can have applications. For example, कोई EV हमने use करनी है, and there we have some second life batteries. We can use those batteries for a shorter route, but of course उसके भी एक अपने consequences हो सकते हैं. Then we can have the energy storage optimization, in which we can look into for the application of AI. So this is related to the product development, related to the for using AI in battery storage, and how we can integrate the AI for the battery reliability. Yeah, thank you so much. I would like to have one more brief presentation related to e-mobility R&D Center, for which I am working. So I'll come straight to the goals of the e-mobility R&D Center, which is funded by USAID, and the goal was to support the manufacturing, the use of affordable EVs in Pakistan as a mean of combating the climate crisis, urban air pollution, while reducing the dependence on imported fossil fuels. So the objectives are to support the indigenization of EV and battery manufacturing value chain, and to test and characterize EV batteries, motors, and electronics, and also it can help implement the national EV standards and conduct R&D for Pakistan's EV industry. Sorry. Currently, in the center, we are providing EV-related technology transfer and professional training, and we are also developing and assessing the commercial viability of the EV solutions. As I've also mentioned before that, we are running pilot field trials for the EV-enabled use cases. We are also developing EV and battery management software, and also formulating the effective EV policies and regulations. So this is the battery testing equipment. Coming up for the battery testing. Then there is the EV motor testing, in which we are using the chassis dynamometers to test the EVs, EV motors, while they are still on, while they are installed on the EVs.
Yeah, in this case, I very this one does not have this.
So that was just a sample of that testing which we were doing, and this is the pilot project in Multan. And also, I'm also leading this project as well. We have 20 rickshaws working there, and the different drivers are actually using those rickshaws. And we have like large amount of data coming up from that pilot project. It's a very useful data, and so basically, e-mobility R&D Center, if anyone of you is interested in working with this center, we welcome you, and you can have the access to the data, to those testing facilities. And thank you so much. This is it from my side. If you have any questions, please do answer, or do ask me. Thank you. So. Yes. हाँ जी.
आपकी मेंटेनेंस प्लान है,
जी जी
इसका कोई हेल्प देगी हमें?
ये आजकल जो रिसर्च ज़्यादातर इसी में हो रही है, क्योंकि रोज़ाना बेसिस पे जैसे सोडियम की बैटरीज आती है, कोई नई केमिस्ट्री वो इसमें ले आते हैं, कोई ना कोई रोज़ाना की बेसिस पे, डेली बेसिस पे आप कोई न्यूज़ देखेंगे कि आज ये मटेरियल उन्होंने डिस्कवर कर लिया है कि ये कर सकता है, कुछ कॉम्बिनेशन
इसको
है
कैसे कोरिलेट करेगी
ये इसके साथ
मटेरियल सिलेक्शन और मेंटेनेंस में कोरिलेट करेगी?
इसमें डिग्रेडेशन पे डिपेंड करता है ना, कि किस में कुछ अंदर जो इंटरनल लिथियम लॉस ऑफ लिथियम इन्वेंट्री होता है, जैसे वो मटेरियल जो है आपका इंटरकलेशन वगैरह उसके लिहाज से उसको देख रहा होता है। डेंड्राइट्स बन जाते हैं, किस मटेरियल में डेंड्राइट्स नहीं बनते, कहाँ पे शॉर्ट सर्किटिंग नहीं हो रही, सो उसमें मटेरियल्स का काफ़ी ज़्यादा रोल प्ले हो जाता है और एआई उसमें काफ़ी वो कर रही है। जी जी
Yeah, I have a similar question.
जी जी
I'm Dr. Jamal from Chemical Engineering from University of Thermal Runaway. Yeah. What sort of model are they directly related to the materials or they are related to the energy produced in the battery?
नहीं, ऑपरेशनल पैरामीटर्स जस्ट लाइक उसमें टेम्परेचर, वोल्टेज, करंट के लिहाज से हमने वो देखे थे, मटेरियल से लिहाज से नहीं, बिकॉज मतलब मैं इलेक्ट्रिकल इंजीनियर था, तो मेनली हमारा फोकस उसके इलेक्ट्रिकल पैरामीटर्स पे था, बट ऑफ कोर्स देयर इज
I
अ
think this is a very important.
yes it is it is
Because उसी की basis पे आपकी heat generate हो रही है.
या मैं क्योंकि मटेरियल्स पे बहुत ज़्यादा नहीं मैं डेप्थ में गया था, बट आई थिंक आप एज अ केमिकल इंजीनियर यू नो द EIS इलेक्ट्रोकेमिकल, वो भी मैंने स्लाइड मैंने निकाल दी थी, उसको मैं अपेंडिक्स में ले गया था, बिकॉज मुझे पता था पता नहीं बहुत डिटेल में ना चली जाए, बट फ्रॉम द EIS थिंग यू कैन एक्चुअली हैव अ लॉट ऑफ ये कोरिलेशंस विद द बैटरी डिग्रेडेशन।
हाँ, इससे तो आपको ये सारा डेटा
यस यस
क्योंकि जैसे अभी आपने बताया स्लाइट वेरिएशन इन द सोडियम टू लिथियम और
हाँ जी, हाँ जी।
कंपोनेंट आपकी एनर्जी जनरेशन द रेट और ये सब कुछ वेरी कर जाएगा।
हाँ जी, उसके अंदर EIS के अंदर हम उसको इलेक्ट्रिकल सर्किट में कन्वर्ट कर लेते हैं, 2RC सर्किट यूज कर लेते हैं हम, जिसके अंदर बहुत बड़ी रेजिस्टेंस होती है, डिफ्यूजन है, चार्ज ट्रांसफर रेजिस्टेंस है, उससे कोरिलेट हम उसको पैरामीटर्स को फिट कर लेते हैं। लेकिन अगर कोई केमिकल इंजीनियर उसको या केमिकल इंजीनियर को इसको देखे तो उसके लिए बहुत ज़्यादा उसमें
Thank you very much for the talk. थोड़ा सा आप ये एक्सप्लेन करेंगे कि for battery swelling and other problems, what kind of strategy you have to collect data for proper modeling? It's going to be a hard. But you have, I think you have a lot of facilities.
हाँ जी, श्योर। सो इसका एक्सपेरिमेंटल डिजाइन वगैरह भी है। सो व्हाट वी हैव इज के वी हैव लाइक डिफरेंट सॉर्ट ऑफ बैटरीज, लाइक जिसमें डिफरेंट केमिस्ट्री की बैटरीज हैं, हम उसके पर बैटरी साइकिलर के साथ उसको रन करते हैं, एंड वी जस्ट उसको 300 साइकिल 400 साइकिल तक हम उसको करते हैं। उसके बाद हम हर 20 या 10 साइकिल्स के बाद व्हाट वी डू इज के हम एक तो EIS वाली चीज़ है, इलेक्ट्रोकेमिकल इम्पीडेंस स्पेक्ट्रोस्कोपी, उसमें उसके कर्व्स वगैरह आ जाते हैं, जिससे हम डिफरेंट रेजिस्टेंस पता लगती हैं, और मेनली इम्पीडेंस, उसकी इंटरनल इम्पीडेंस भी पता लगे। सेकंड है कि उसकी कूलम काउंटिंग के थ्रू हम उसकी कैपेसिटी वगैरह देख लेते हैं, मतलब एक कैरेक्टरिस्टिक साइकिल भी हम रन करते हैं आफ्टर 10 साइकिल्स, कि उससे उसकी कैपेसिटी पता लगे, डिस्चार्ज कैपेसिटी क्या है। देन उसकी हम ऑफ कोर्स मेजरमेंट्स, अल्ट्रासोनिक सेंसर, हमने 3-4 तरीके थे, 1 ईयर कैलिपर से भी हम उसकी स्वेलिंग को देखते हैं, अल्ट्रासोनिक सेंसर्स के थ्रू हम उसको हमने सेंसर लगाए थे, उससे भी हम देखते हैं। तो हमारे पास मेनली ये 3-4 पैरामीटर जो है ना वो डिपेंड। हाँ, उसके अलावा आपकी सी रेट्स, आप किस सी रेट पे उसको चार्ज डिस्चार्ज करवा रहे हैं, हमने टेम्परेचर को भी देखा उसके अंदर, सी रेट पे भी देखा मेनली जो, और मजे की बात एक और है कि हमने पोर चार्ज भी करके देखा, मतलब हमारे पास 2 कंडीशन थी, चार्ज स्टार्ट एट हाई सी रेट, और दूसरा हमारे पास कुछ बैटरीज ऐसी होती हैं जैसे नोकिया के पुराने मोबाइल थे जो लगे रहते थे, लोग कहते थे ओवर चार्ज हो गया, बैटरी फूल गई, हमने वो सिनेरियो भी किया उसके अंदर, और उसमें भी उसको रूम टेम्परेचर पे और एक 45 डिग्री सेंटीग्रेड पे भी हमने करके देखा, जिसमें हम जैसे बैटरी की रेटेड वोल्टेज 4.2 थी, तो हमने उसको 4.23 पे होल्ड करके रखा, जो कि वो बैटरी का जो कि पाउच सेल बैटरी थी तो वो होल्ड करने दे देती थी क्योंकि उनकी रेटेड, तो 4.23 वोल्ट्स पे एट 45 डिग्री उसकी सबसे ज़्यादा स्वेलिंग थी, और वो हार्ड मतलब 40 to 50 साइकिल के बाद भी काफ़ी ज़्यादा उसकी परसेंटेज बढ़ गई थी। लेकिन मेनली जो हमने नोट किया था कि अगर हम इतना अगर उसको ओवरचार्ज ना भी करें, बट द टेम्परेचर वाज द मेन फैक्टर कि 45 डिग्री और 4.2 पे भी होल्ड करके देखें तो हम वहाँ पे हमें स्वेलिंग काफी मिली। सो डिफरेंट पैरामीटर्स, वोल्टेज, आपका सी रेट, टेम्परेचर, आपकी इंटरनल इम्पिडेंस, आपकी कैपेसिटी, उससे आप स्वेलिंग को कर सकते हैं। और ये ऐसे पैरामीटर्स हैं विच यू कैन एक्वायर वेरी इजीली। तो इस तरह का बैटरी डाटा जो है ना वो हमने उसको हमने टारगेट किया।
Project that you're running with Sazgar in Lahore and Multan.
मुल्तान दोनों में
In दोनों में. So, what is the output so far? Is it getting accepted properly? Are the drivers earning? And what is the from financial perspective? Is it becoming successful?
अच्छा, सबसे पहले तो हमें रिक्शा ड्राइवर्स को ऑफ कोर्स हमें उनको कन्विंस करने में बड़ा एक तो मसला होता है। उनकी फाइनेंशियल ट्रेनिंग बहुत ज़रूरी है। उनको आप टेक्निकल चीज़ें जो मर्जी बता दें, बट जब तक आप उनको खुद एक एग्जांपल सेट नहीं करेंगे, तो एग्जांपल नहीं बताएंगे, तो हमें वो वैल्यूज़ बड़े एक लेमैन के फॉर्म में उनको पास लेकर जाएंगे। हम उनको जैसे बताते हैं कि जी पर किलोमीटर आपको जो पेट्रोल का रिक्शा पड़ता है वो 16 रुपीज़ का पड़ता है, इंक्लूडिंग द मेंटेनेंस, ऑयल चेंज, ब्रेक ऑयल वगैरह। जो आपको जो एलपीजी वाला पड़ता है वो हार्डली मतलब 12 to 13 रुपीज़ पड़ता है। और जो इलेक्ट्रिक रिक्शा जो हमने उनको दिया था उसकी सारी कॉस्ट एनालिसिस हमने किया, उनको कहा कि पर किलोमीटर आपको ये 6 से 7 रुपए का पड़ेगा। अब मसला उनके लिए सिर्फ एक जो आ रहा है, उनके पास वो स्टेशन का मसला आ रहा है कि स्टेशन, क्योंकि हमारे पास सिर्फ 2 स्टेशन हैं, एक बिल्कुल शहर के अंदर है इन मुल्तान और एक थोड़ा शहर से बाहर है, एमएनएस यूनिवर्सिटी है उसके बैक साइड। तो मेनली उनको ये है, उनके पास अब डेड माइलेज बहुत ज़्यादा है कि उनको रूट लिया है उन्होंने, अब जरा साउथ की तरफ जाना है, बट हमारा अगर दूसरी साइड पर है स्टेशन तो वो वाला पैसेंजर नहीं ले सकते। अदरवाइज पैसेंजर्स का जो फीडबैक है उसमें उनको साउंड और नॉइस से रिलेटेड वो बहुत कंफर्टेबल है। बाकी तो आम रिक्शा तो इसी तरह नहीं है, जो 7 घर का मेरे को बाइक भी खड़ा हुआ है, लेकिन इसी चेसिस यही है, बट अंदर जो उसका सिस्टम है इट्स अ बिट डिफरेंट। और कॉस्टिंग का मेनली आपको कन्विंस करना पड़ता है। उनको एनवायरनमेंट से रिलेटेड कोई कंसर्न नहीं है रिक्शा ड्राइवर्स को भी। हाँ, लेकिन हमने उसको रेंट मॉडल पे दिया, रेंटिंग मॉडल, क्योंकि हमारे पास यूएसए की फंडिंग थी, हमने इसको पायलट प्रोजेक्ट पे चलाना था। सो हमने उनको ये नहीं कहा कि आप हमसे खरीदें, हमने उनको डेली बेसिस पे जो रेंट पेट्रोल या एलपीजी को देते हैं वो 400-500 देते हैं, लेकिन हम उनसे 300 या 300-250 इतना हम उसको चार्ज करते हैं। और उसमें भी फ्लेक्सिबिलिटी हम दिखा देते हैं कि चलें, लेकिन मार्केट डिस्टॉर्ट नहीं कर रहे हम। मतलब ये नहीं चाह रहे कि हम उनको मुफ्त रिक्शा दे दें, मुफ्त एनर्जी दे दें। अब वो बैटरी की एनर्जी, जब वो एनर्जी बैटरी स्वैप करवाने आते हैं तो हमने पर पर्सन कॉस्ट रखी हुई है। मतलब फॉर एग्जांपल आपने 90 से लेकर 80 तक यूज़ किया है, सो पर पर्सन वी हैव फिक्स्ड अ कॉस्ट ऑफ लाइक 5 to 6 रुपीज़। और वो हमारा कॉस्ट एनालिसिस था जो मॉडलिंग की थी, तो उस लिहाज से, क्योंकि हमने अपना भी थोड़ा सा मार्जिन रखना था उसमें और उनको भी बेनिफिट।
अच्छा, इसमें एक चीज़ और समझाने की कोशिश कीजिएगा, हमें बताने की कोशिश कीजिएगा, क्या इसकी पॉलिसी अलाउड है कि आप 10 सीटर्स साजगार रिक्शा बना सकें पास? पंजाब में तो अलाउड नहीं है
इलेक्ट्रिक रिक्शास
10 सीटर रिक्शा, चाहे साजगार जो बना रहे हैं बैटरी बाइक आपका काम कर रहे हैं, लेकिन पॉलिसी में कितनी चाहिए?
नहीं, हमारा 10 सीटर नहीं है, हमारा 4 सीटर ही है।
ये तो आपके जो अभी हैं वो 6 से 10 वाले भी बता रहे हैं आप लोग, उसमें तो पॉलिसी में नहीं है अलाउड।
नहीं, अभी नहीं, हम वो नहीं कर रहे। जो अभी पैसेंजर रिक्शा चल रहे हैं वो 4 सीटर, और जो लोडर रिक्शाज हैं, लोडर रिक्शाज में एक्चुअली दे हैव अ वेरी बिग कार्गो एट द बैक, और रजिस्ट्रेशन वैसे उसकी ओपन स्टार्ट तो हो गई है।
रजिस्ट्रेशन हो रही है, लेकिन ये अगर हम आप ऑडियंस को थोड़ा उसके लिए अलाउ हो गया पंजाब गवर्नमेंट की?
नहीं, अभी हो रहा है, अभी इन प्रोसेस है, उसको थोड़ा टाइम लगेगा। सो हमारे रिक्शा भी अभी, आपको पता मुल्तान जरा छोटा शहर है, वहाँ पे नहीं पकड़े जाते, लेकिन जो पकड़े जाए फिर वो चलान दे देते हैं, फिर हम उनको कवर कर देते हैं। सो दैट्स हाउ इट इज। इससे रिलेटेड कोई और भी क्वेश्चन है तो मतलब यू आर मोस्ट वेलकम। क्या
We use the batteries at home.
Yeah,
How are they connected with information technology like computer? Sir, I have just a general question. Like the batteries which we use for electricity at home, how they are connected with softwares and artificial intelligence?
अच्छा,
Like generally, please reply. Thank you.
Sure. जो आपकी ऑफ कोर्स यूपीएस की जो बैटरीज है, दैट्स उसकी चार्जिंग डिस्चार्जिंग इज कंट्रोल्ड बाय द यूपीएस, एंड उसके अंदर माइक्रो कंट्रोलर कुछ ना कुछ वो ऐसा लगा हुआ है। बट फॉर द लैपटॉप उसके अंदर भी कुछ ऑप्टिमाइजेशन सॉफ्टवेयर होते हैं, जैसे आपकी बैटरी सेवर वाली चीज़ आ जाती है जिसमें एप्लीकेशन को वो बंद कर देता है पीछे, या आपके जो बैक एंड पे एप्लीकेशन चल रही है उनकी ज़रा यूजेज को कम कर देता है इफ़ यू टर्न ऑन द बैटरी सेवर। एंड बट AI फॉर ये जो EVs के अंदर, इसमें थोड़ा सा इशू ये है कि जो EVs का यूजेज है ना, इट्स वेरी ड्रास्टिक, एंड व्हेन यू एक्सेलरेट द बैटरी बहुत हाई करंट उसको लेना पड़ता है, एंड देन यू हैव टू सी कि अच्छा, और एक्चुअली बैटरी की उसमें बैटरी जो होती है वो बहुत हाई कैपेसिटी की यूज हो रही है, सो उसमें इतना ज़्यादा रिस्क ज़्यादा इन्वॉल्व है बजाय कि जैसे लैपटॉप हैं या मोबाइल फ़ोन्स हैं। ऑफ कोर्स इसमें भी मोबाइल फ़ोन्स के अंदर भी सेफ्टी रिस्क हैं, आईफोन के अंदर और बाकी डिफरेंट मोबाइल के अंदर भी हमने स्वेलिंग नोट की थी। हमने वी एक्चुअली रन दोज एक्सपेरिमेंट द आईफोन एज वेल, इसमें भी स्वेलिंग हुई थी, और हमने इन चीज़ों ऑफ कोर्स वो डिफरेंट कंडीशन डिफरेंट थी बट हुई थी। अगर कोई वेपिंग करता है, वुड हाईली रिकमेंड कि ना करें, क्योंकि हमारे पास बड़े सिंपल केसेस में भी बड़े वो फट जाते थे। सो इट्स ई सिगरेट्स और ये वाली चीज़। तो आपका क्वेश्चन मेरे ख्याल से ये हो गया कि क्योंकि दे आर वेरी हाई डेंसिटी एंड हाई कैपेसिटी बैटरीज, तो उनके लिए ज़रा और एक रॉबस्ट किस्म का सॉफ्टवेयर वगैरह उसमें रिक्वायर्ड होगा। इसके अलावा if anyone wants to do any work for the e-mobility in the e-mobility R&D center and
मेरा क्वेश्चन है आपसे मशीन लर्निंग के बारे में कि आप मशीन लर्निंग की कौन सी टेक्निक यूज़ करते हैं और उससे बैटरी की क्या हेल्थ आप डिटरमिन कर रहे हैं, क्या कर रहे हैं? क्योंकि वोल्टेज और करंट या लेस से उसका वोल्टेज लेवल या बैटरी के करंट से भी बेसिक तो आपको पता चल जाता है, तो फिर आप क्या क्लासिफिकेशन यूज़ करते हैं मशीन लर्निंग में या क्या यूज़ कर रहे हैं?
नहीं, हम सुपरवाइज लर्निंग ही है, उसमें ज़्यादा इंसेंबल मेथड्स यूज़ करें, जैसे रैंडम फॉरेस्ट है, एक्सजी बूस्ट है। इसके इनके रिजल्ट ज़्यादा अच्छे थे बजाय कि हम, क्योंकि डीप लर्निंग तब यूज़ कर सकते हैं जब हमने स्टेट ऑफ चार्ज को एस्टिमेट करना हो। स्टेट ऑफ चार्ज, स्टेट ऑफ हेल्थ इज अ डिफरेंट थिंग। अभी जैसे मेरे मोबाइल की जो बैटरी परसेंटेज है वो 91 है, इट्स अ स्टेट ऑफ चार्ज प्रोबेबली, ये उसके इंडिकेटर। बट बैटरी हेल्थ जैसे मेरी मोबाइल फ़ोन की, उसका डाटा थोड़ा सा हमारे पास कम होता है। ऑफ कोर्स जब डाटा कम है तो उसमें हमको डीप लर्निंग या न्यूरल नेटवर्क्स की तरह कम उसमें इतना नहीं यूज जाता, क्योंकि और मसले मिसाल ओवर फिटिंग के इश्यूज आ जाएंगे। सो हमारे पास जो मेनली इसमें एनसेंबल मेथड्स हैं या हाइब्रिड मेथड्स हैं, वो डिग्रेडेशन के लिए बहुत अच्छे यूज होते हैं, जिसमें पार्टिकल फिल्टर को आप मशीन लर्निंग के साथ इन किसी और आपके ये कैलमन फिल्टर वगैरह इनको आप इंटीग्रेट कर सकते हैं। डिफरेंट मशीन लर्निंग जो एनसेंबल मेथड्स हैं स्पेसिफिकली, उनके साथ दे कैन एक्चुअली परफॉर्म वेरी वेल। Any other question, please? ठीक है, thank you so much जी।
Thank you, sir, for your informative talk. We would like to invite Dr. Kashif Imran to present the senior to Professor Dr. Zafar Rao. Our second invited talk is Energy and Power Policies of Benefits of Utility Grade Battery Energy Storage Systems for Investor and System Reliability by Dr. Kashif Imran from NUST. Please welcome Dr. Kashif Imran with big round of applause.
Bismillahirrahmanirrahim. Assalamu alaikum. My name is Dr. Kashif Imran, and I have been at UAT campus for a very long time. In fact, I was here first time in 1985 as a child living in the staff colony. So I have a very long memories of UAT Lahore. I've done my bachelor's and master's while staying on campus in the colony. And I moved. After my graduation in 2006, I started working in UAT Lahore as a faculty member at that time. But then I moved to Siemens and later to NESPAC. For a while, I was in NESPAC. I worked as a design engineer in electrical distribution section. I was working with Zagam Isa Khan was my immediate boss. He is currently MD NESPAC. Learned a lot from him. Worked on a lot of projects. We designed electricity, energy distribution systems for a variety of buildings and for many projects. So it was a wonderful time in Lahore, and then I switched to ComSets Lahore. I worked in ComSets Lahore for quite a long time, and I went for my PhD from ComSets Lahore. I was on leave from ComSets Lahore, but I got a Commonwealth scholarship, so there was no bond on me, so I was free to move around. So when I came back, I joined ComSets Lahore for 1 year, but then I moved to NUST. Because in Islamabad, NUST started a US-Pakistan Center for Advanced Studies in Energy in 2013. So by the time I was here in 2016, it was very mature, and they were planning to start their degree in electrical power engineering as well. Because they had, until then they had only energy systems engineering or renewable energy engineering or another degree called thermal energy engineering. So we at US Pakistan Center for Advanced Studies in Energy, we are a graduate school. We only have master's and PhD programs, but by 2016 they wanted to start electrical power engineering, MS, and later PhD, but they didn't have faculty. So it was really great to be there and to work there and to build the center. I'll just introduce myself a little bit and my center, because I don't have any slides on that, and then we can move on to the presentation. So at US Pakistan Center for Advanced Studies in Energy, we have a high voltage lab. It is state-of-the-art lab. It has the same equipment as we have in Rawat. So we have Hafele equipment by Hafele, Switzerland. It costed us $1 million. I was heading that lab. So I was founding principal investigator of that lab. It has a dedicated building and everything. So it is now working, is functional now. We also have other research labs. So we do not have any teaching labs at USPCAS, at US Pakistan Center for Advanced Studies. We are located in H12, sector H12 of Islamabad. So we are at the main campus or the civilian campus, because NUS, as you know, also the College of Electrical and Mechanical Engineering and the College of Aeronautical Engineering, they also fall under NUS, but they are separate campuses. So at our civilian campus, we have a dedicated building of USPCASI, and we have smart grid lab where we have hardware in the loop capabilities, so we can have testing for hardware if we are developing, if a company is developing, for example, an inverter for a specific market. For example, Sky Electric is a big name in PV, and they are developing some inverters for, let's say, Japanese market. So they need to test those inverters before they introduce them in the Japanese market, and they need to test them under certain specific grid codes. So they come to us, and we offer services, such commercial testing services in those labs. So those are testing as well as research labs. So our students can also get hands-on experience on the hardware in the loop and all kinds of things. So we have FPGA-based national instrument equipment where you can develop, for example, protection relays that are prototypes, and you can develop them using the LabVIEW software. So these are the kinds of labs we have. We also have, so these are the labs that are directly related to electrical engineering. Other than that, we do have renewable energy labs, a number of them. But we have another lab, which is PV testing lab. So this is again a testing lab and also used for research. So this is some of the things. This is some introduction about USPCASI, where I have been since 2016. So I joined there as assistant professor. I was promoted 3 years ago or something to associate professor, and I was inaugural head of the Department of Electrical Power Engineering. So now I will talk a bit about my research, and then we'll move on to the presentation that we have particularly today. So my research is quite it is happening in multiple areas. Like so, I'm also working on energy policy and planning. So some of my research falls in power system protection. So we use Kalman filters and other DSP and machine learning techniques to develop microgrid protection schemes. And other than that, I'm mainly interested in power system studies. So for power systems, if we need to do planning, if we need to do how to place FACTS or the phasor measurement units or energy storage systems optimally in a power system, then how to find the location and how to find the sizes of battery energy storage systems, for example. So this is my main area, power system studies, power system planning and operation studies. So my PhD is in electricity markets. So electricity markets are like, you can imagine, they're like software of the hardware that we know as power systems. So power systems remain the same, but how we trade energy, that changes, and that can change, and that is evolving in Pakistan as well. So we have Central Power Purchasing Agency that was once part of the WAPTA or NTDC, but now it's a separate entity. It's handling the evolution of electricity market in Pakistan. Although so far the measures are just like, they're not drastic, but hopefully we'll get there. So this is my introduction and my research. And now let's move on to the particular topic. So today we will discuss how to optimally, this is one of the research papers that we have published. So it is an ongoing research. We are working on some aspects of it. So you are aware that, so this is just background. So we know that batteries are a requirement for us because we have a lot of renewable energy in the system, but it is intermittent. So it's best to have battery energy storage systems in the network. So we can have different studies. We can have studies of battery energy storage systems deployment in distribution grid. That will be different. That will have different dynamics. But if we want to deploy battery energy storage systems in transmission grid, then we'll have slightly different things. So move on to the next slide. Will you move to the next slide, or can I move it? Okay. Yes. Is it fine? Okay. So if we want to deploy BESS, we need to take care of its cost because it's very costly equipment. So the best thing is to do it optimally. So for the purposes of optimal BESS deployment, we need to first of all study the system. We need to look at the system, and the optimal locations for battery energy storage system will vary from system to system. So because we know that battery energy storage systems can have different benefits for our grid. They can improve the quality. There are many applications, but this study is mainly focused on improving the reliability of the grid. Reliability of the grid through deployment of battery energy storage systems. So the main question that we will look at are the location, sizing, type, and payback period of BESS, and how we can assess how we can deploy battery in an optimal way. So in this study, in this presentation, we'll talk about how to develop case studies and how to run studies in MOST. So MOST is a tool in the MAT Power. So MAT Power is a well-known MATLAB-based tool that can be used for system studies that are not dynamic. It can be used for load flow and for optimal power flow. So we'll use the MAT Power tool, and specifically its MOST tool, which is MAT Power Optimal Scheduling tool, which is a multi-period unit commitment type of thing. And within that, we have option to include BESS. So since we did a reliability test system, since we did a reliability study, we used a reliability test system, and we studied on that. There are multiple approaches if we want to determine the location. So there are many ways, but we use two approaches. And the first approach involved the co-location of BESS with wind and solar generators, because we know that wind and solar are intermittent and they are available at those locations. So it's best to avoid any losses, and we can put them right where the solar and wind is. That's one approach. And the second approach is to do a load flow based study and find out those locations where placing BESS will reduce the losses, will minimize the losses in the systems. And that is the second approach. So there's some mathematics for the sensitivity factor approach. That is the second approach that we use. But there are many other methods. There are multiple methods, and they can be used for finding out the location. So sometimes we can use optimization algorithms that are so comprehensive that they are finding out, they have decision variables of the best locations as well as best sizes. So they give both of those things at the same time. But we adopted a sequential approach where we first determined the optimal locations, and once we knew the optimal locations, then we determined their optimal sizes and types. So here we have MATPower, which is a open source simulation package for power systems. It is based on MATLAB, and we can do load flow and OPF in it. And MOST is a tool within it, which is more comprehensive than MATPower, and it is MATPower Optimal Scheduling Tool. So in MOST we can do a stochastic as well as deterministic studies. We can have stochastic scenarios, or we can do deterministic studies, whichever one works for us we can do. So in MOST it is possible to do 24-hourly studies. And we did 24-hourly studies to see which storage size is best for us. So MOST is included in the latest version of BESS is included in the latest version of MOST. So we can introduce our BESS unit as a generator, and we can define its power and energy ratings, and then it can be dispatched. So main thing in BESS is that we work on something called energy arbitrage, or the price differences. So in for example in European or US markets, there are hourly prices. So prices vary from hour to hour. So we have certain hours when the prices are very low, and then we have other hours when the prices go very high. So BESS normally operates, if BESS is operating, BESS is owned by a private investor, then BESS will operate on the principle of energy arbitrage, which means they will charge at they will find out those hours, they will forecast those hours when the energy price is expected to be very, very low, and then they will charge in those hours so that they have their charging capacity, and then when it comes to high priced hours, only then they will discharge. So this is called energy arbitrage. So we can have two ways. We can have a self-dispatch of BESS if it's owned by a private investor, but if it has been invested in by a system operator, then it will be part of the central dispatch. Then it will be included in the central dispatch problem formulation. So its decision when to dispatch it, when to charge it, or when to discharge it depends on the central optimization algorithm. So in this study that I'm presenting, we worked on both aspects. So that is from the central dispatch point of view as well as self-dispatch point of view. So when we are doing self-dispatch, we are only concerned with energy arbitrage, making money out of BESS. But when we are doing central dispatch, we are also concerned with improving the reliability of the system, reducing the overall operational cost of the system. As you are aware that's what unit commitment does, that's what OPF does. So talking about reliability in power systems, there are multiple reliability indices, and some of them are very common. They are listed here, like loss of load probability, and they have their definitions right in front of you. So there are loss of load probability, loss of load expectation. So there are multiple reliability indices. And there's a new one, value of loss load at the bottom. It's not so common, you may not have heard of it. It's used in electricity markets. So value of loss load is determined by surveys from the users. So you go and ask the users and say, what is the value of loss load to you? How much do you value the load? How much do you value the energy continuity? If there is a discontinuation, what will be the loss to you? So it's determined on the basis of those surveys. So there are multiple reliability indices that we determined, and we used frequency and duration Monte Carlo using MATLAB. So in the grid code, for example, in the ICECE in Pakistan, the indicative generation capacity expansion plan, there are specific values of loss of load expectation and the others. So they are defined that you should design a system such that its reliability meets certain criteria. Its reliability, it's reliable up to a certain standard. So we need to be so the system planners design according to that. So in our study, we also took care of these standards. So we developed multiple case studies, and we can say that. So we developed multiple case studies, and in the base case, I will skip this because we have another flow chart coming up, and that is more appropriate. So we'll skip it. In this slide, we can see that we are showing you a mathematical model for optimal battery deployment. It's not a very complicated model. It's a simple equation. We are determining the net benefit function of a private investor. First of all, if there is a private investor and it is investing in BESS, then its net benefit BPI, will depend on the savings it is going to make from the battery, because when it is going to charge, it is going to cost it, and only when it discharges, it's going to make some money. So overall, it is expected to have some saving at least, because it is going to charge in the low priced hours and it's going to discharge in the high priced hours. That's why we expect that it will have some saving. And at the same time, it needs to take care of the initial cost or the total cost of installing BESS in the system. Because we are talking about 100 megawatt BESS systems deployed in transmission system, which are very costly, and they will have a payback period. They may have payback period of many, many years. So having this equation, where you can see the energy arbitrage I was talking about is being calculated here over 24 hours. So we have the savings, where the LMP stands for locational marginal price, because for example in US markets the price changes from location to location. For example, you do optimal power flow in power system studies and you find out lambdas. The lambdas are the locations at specific nodes or specific locations. So that is the system of pricing used in USA. In Europe, for example, we have same prices throughout the country. But we have locational marginal prices so that will be the location of the BESS. That is the price at the location of the BESS. And then we have a charging or discharging volume. So whether it's charging in a particular hour or it's discharging, it depends. So if it's charging, if a BESS is charging, then it will be a cost. If it is discharging, then it will be an income, revenue for the battery. So overall, the algebraic sum will give us this saving by operating that battery. And remember, we are talking about the private investor. So the private investor is only concerned about the cost it has incurred in installing the BESS, and whatever is going to make, or whatever money is going to make out of that investment. So it's not concerned about system reliability indices or any power losses. So here nothing is included. And so this way, so the cost of battery installation will depend on a number of factors like fixed O&M, variable O&M, and all other things. So this is a mathematical model that we used, and here you can see we studied for 4 different types of batteries: lithium-ion LFP, lithium-ion NMC, and also lead acid and the vanadium redox flow. we considered these four types of batteries. And it is important to remember that the total cost depends on multiple factors. The total cost of BESS depends on the storage block, storage balance of system, power equipment controls and communication, all of those things, and as well as leading up to the project development and grid integration costs. So all of those costs are collected together, and that is total installed capacity, total installed cost in dollars per kilowatt hour for each kind of technology, BESS technology. So it varies from BESS technology to BESS technology. And so, and their lifetime in years is given in specific reports, for example, reports by National Renewable Energy Laboratory of USA, and it is available, that kind of data is available for one charging discharging cycle each day. And depending on that, we can see that if we use lead acid batteries, we'll need to replace them very often. If we are covering a period of 15 or 16 years, they may need to be replaced 8 times, as compared to the vanadium redox flow batteries, which are very expensive. They have a cost of $399 as compared to $356 for lead acid, but you don't need to replace them. That's the good thing about them. And there are in between, we have the lithium-ion batteries, and these are the most popular batteries as far as best deployment for of grid-scale batteries is concerned. These are the most popular batteries, lithium-ion batteries. And now let's talk about the net benefit function of system operator. So again, we have similarly the savings that the system operator will make, because now the system operator has invested in the battery. It will have its own cost as well. But now we can have a loss factor, where loss factor LB is calculated by expected unserved energy multiplied by number of days per year, multiplied by number of years, multiplied by volume of lost load. So that's how we use two reliability indices, expected unserved energy and value of lost load, together to quantify the impact of battery on a system. So otherwise we don't have. So with the help of value of lost load, which is in dollars per megawatt hour, and expected unserved energy, which is in megawatt hour, let's say, so then you get a dollar amount, so we can put it in the net benefit function. So this net benefit function is different, and it is also different because the savings of system operator are now not being determined by the energy arbitrage or by the battery of charging in the low price hours and discharging in the high price hours, but now we are talking about unit commitment based optimization. So if we have, here we can say, if we do not have any BESS, if we do not have any battery energy storage in the system, then we run most, and we get a cost function. We get an objective function value, which is a particular cost. So expectation is, if we introduce BESS in the system, then what will happen? We will have to dispatch less thermal generation, and that will mean our objective function value will decrease. So we will have a better optimization, and that means the value of OBV will be less as compared to the, if we are minimizing, there will be a difference, there will be an improvement. So this is how the objective function for the system operator was developed. So here is another flow chart of our methodology that is more clear. So once we start, for each BESS node, where we are going to place the BESS, because remember, we have determined the optimal BESS locations already by the initial in the earlier phase, and then we, depending on whether it's charging or discharging, and depending on the locational marginal price in that hour, we can have an algebraic sum, and that can give us savings for the private investor, PI. SPI means savings for the private investor in battery. And at the same time, we can have, considering all the total BESS cost involved, and depending on the battery technology we have selected in the particular iteration, we can find out total cost. And then having this total cost, we can determine the net benefit function of the system operator, as well as the net benefit function of the private investor. And in both cases, there are little difference in the formulation. In And because we use the reliability indices of expected unserved energy and value of lost load, we can collect them together into a dollar amount, and then we can plug into the for calculating the net benefit function. So we can continue this process until the storage, because we are talking about battery energy storage systems and we do not have any idea. I will talk about 3 phases of optimal best sizing. So that's the main thing. We'll talk about 3 stages, but this is the overall idea that once we have explored one technology, one best technology, then we move on to the next best technology and so on. So as I talked earlier, we have used IEEE Reliability Test System, RTS, which is used for reliability studies, and it has a number of generations of different technologies. So this test system is particularly used for reliability test studies. It is called RTS GMLC, Grid Modernization LC. So it has been, this particular test system has been growing over the years. Initially it was a very small one, but it didn't have any renewable energy plants in it, and it was only based on thermal energy plants and so on. But now the latest RTS GMLC model was provided in 2019, and it is much more sophisticated as compared to earlier versions of this test system. So here is the summary of the conventional generators that are available in the reliability test system. So you can see all kinds of generation technologies are represented here, so that any studies in this reliability test system are representative of, can work for a real grid as well. So we have another table here that is showing the renewable generators that are available in the, that are included in the reliability test system. So this is how it looks like. This reliability test system has 3 regions and it is spread over a large area. So 3 case studies are presented in this slide. So our first criteria for choosing the location of BESS was based on where the PV or the wind was available. So right of those, we just randomly selected this. This is not optimization. The third case study involves optimization. In the first case study, we randomly selected. We just went for those locations where there was a lot of wind or PV. So these 3 nodes were selected. And in the second case study, again, there were 3 buses were chosen, and at those buses there were wind installed capacity. There was a huge wind installation over there, 847 megawatt and so on. But in the third case study, optimal location was determined using a sensitivity index, using the load flow. It was a load flow based study. So we determined, first of all, which are the optimal locations where by placing BESS, the system losses will be reduced. And then we installed BESS over there. So that is the Z-bus matrix method. So here are the 3 exploration phases, because once we have determined the optimal locations, we need to determine the optimal size of the BESS. So for that, we did not develop any optimization algorithm as such. We used the optimization inbuilt in the optimal power flow, but we developed a 3-phase strategy where we depended on the reliability indices, which we have talked about, loss of load hourly, loss of load probability, and so on. We depended on them in the first phase to find a region where we expect to find optimal battery size. That was the first phase. And then In the second phase, we narrowed down the search space by using the net benefit functions that I have talked about. And in the third phase, we found the exact battery size that will be optimal. So when we determined optimal location on the basis of sensitivity factor, Z bus sensitivity factor, we determined that these buses are the optimal locations. The bus number 321 being the most optimal, and then this being the least optimal in this list. So if we are going to install three beds, we can choose these 3 locations, and that will be the best location. And if we have more investment, we can choose 5 or so on. So using the Monte Carlo simulation method for calculating reliability indices in MATLAB using available code, we determined a number of reliability indices. For example, expected unserved energy. And in case of expected unserved energy, you can see that if we start increasing the battery capacity from 25 megawatt hour to 50 to 100 and so on, then there comes a point where we are able to meet the threshold level defined in grid codes, for example. For example, grid codes say that expected unserved energy should be less than 0.0002. So this is the level. And we see that as we start increasing the battery level, there comes a point where we are able to meet this. So this is the first phase of our exploration. This gave us a clue that at which point it's enough, and we should not invest more in battery, because then we will not be able to recover that cost. So this is the initial phase. We did for expected unserved energy in this slide, and then for loss of load hours, again in this slide again we saw that when we go up to 100 megawatt hour battery, then we are able to meet the minimum threshold specified in the grid codes. So this is how it worked. We explored for multiple indices. This is the next: loss of load expectation and loss of load probability. Loss of load probability is calculated on hourly basis for 24 hours, because we were running simulation for 24 hours. So it gave us, again we can see that all reliability indices do not give us the same result. For example, if we are only looking at loss of load expectation, then even a battery of 200 megawatt hour is not meeting the threshold exactly. It's reaching close to it, but it's not meeting exactly. So there are multiple reliability indices available, but we need to look at the trend. And the trend is most of the reliability indices are satisfied as soon as we reach a capacity of 100 megawatt hour for this system, for this reliability test system. Of course, it will vary from system to system. So once we know that our batteries, if we are going to place 3 batteries, if we already find out their optimal locations, and we realize that they can be close to 100, then we need to fine tune further. We need to go into the next phase of our exploration for optimal solution. And in this phase, what we do is, for all 3 case studies that I was talking about, where the first 2 case studies, we chose the locations arbitrarily for those locations where there was PV and wind. And in the third case, we chose it on the optimal location. In all 3 cases, we determined the net benefit function. You can see as we increase the battery size, the net benefit function increases. But there comes a point where if the battery size is too high, then what will happen? Reliability index is improving all the time. It's dropping down, as I showed you in the previous slides. But the cost is, we're not able to recover the cost. The net benefit of that high battery size is not reaching us, it is going down. So that shows us that this is the optimal point. This is another indication that optimal point is somewhere around 125. Still we are in the same region, we know that. So we are fine tuning our search space, and we are trying to find the optimal location, optimal sizing of the best battery energy storage system. So this is how we have shown the So on this side, we have the net benefit function, net benefit value of the system operator. And in this side, we have net benefit value to the private investor. And for the same battery sizes. So again, you can see there comes the optimal point, and then the net benefit starts decreasing. And even it can go negative sometimes. So this result is for lithium-ion NMC battery. And we also explored these results for other battery types, for the lead acid battery and also for the vanadium redox flow battery. So this was our second stage, and we realized that the optimal battery size is somewhere around 100 and 125 in this region. And then in this last exploration stage, so in the second stage, we were saying that all three batteries, because we are placing three batteries, all of them have the same size. Either they have a size of 100, or all of them have a size of 125, and so on. But in this case, we explored all the different combinations. So we said they can be around 100, 125, or 150, but we are not sure. So let's have, if we are given three values, 100, 125, and 150, and we want to explore all of their combinations, then we get 27 combinations. So out of those 27 combinations, if you keep the first battery as 100 and the other two can be 100, 125, and 150, then we have shown the net benefit functions of 9 combinations, 9 possible combinations here. These are for the system operator and these are for the private investor. And then we know that since we have 3 battery sizes, so there are 27 possible combinations. If we keep the first battery instead of 100, if we keep it as 125, then the other two can vary. But if we keep it 150, then the other two battery size can vary again. So in this case, the combination where the first battery was 125 megawatt, the second was 100, and the third was 100 was the most optimal, and for the system operator, because it provides the maximum net benefits of $164.8 million over a year out of all 27 possible combinations we talked about. And similarly, so by looking at the graphs, by looking at their values, we were able to see which are the most optimal sizes. And if we're talking about the private investor, PI, then the most optimal sizing was 150, 100, and 100. For the same location, so it depends who is investing in the battery. If system operator is investing in the battery, then the optimal sizes are different. And if they are 125, 100, and 100. But if the private investor is investing, then they are different. So it completely depends on who is investing and from what perspectives, because private investor is investing from the perspective of just getting some income, whereas the system operator also wants to reduce this overall system operation cost and improve the reliability of the system, which we are taking care of in the net benefit function of the system operator only. And that includes 2 reliability indices: value of lost load and expected unserved energy. So this is just a summary of what we did. So I can say we used a specific tool which exists in MATPower, which is a MATLAB based optimization framework, and we use MOST, which is within MATPower, which is MATPower optimal scheduling tool. It gives us ability to have steady state power system analysis, including load flow and unit commitment and optimal power flow studies. And we were able to develop a methodology to determine optimal sizing, optimal best sizing for transmission grids. So we determined optimal locations first of all, then we determined optimal best sizes using a three-phase strategy, and then we explored all the best technologies that are currently being used for grid scale BESS. That is lead acid as well. It's not that popular. Mostly it's lithium ion, 2 types of lithium ion, and also vanadium redox flow, but they are very expensive. So This is basically all, and this is the paper that was published in Journal of Energy Storage. Thank you very much. Any questions, please?
So इसमें जो कॉस्ट है वेरिएबल कॉस्ट
जी,
ये सेम है इसकी नहीं इस पर्सन में
ये जो वेरिएबल कॉस्ट है,
जो फोर्थ कॉलम।
हाँ जी, यस यस, इसमें आप कह रहे हैं, हाँ। तो ये जो वेरिएबल कॉस्ट है, ये जैसे मैंने कहा था कि नेशनल रिन्यूएबल एनर्जी लैब जो यूएसए की है,
Yes.
उसने रिसेंटली 1-2 साल पहले, और वो हर 2 साल बाद वो इशू करते हैं एक रिपोर्ट, जिसमें वो देते हैं मार्केट के क्या ट्रेंड्स चल रहे हैं, कॉस्ट क्या चल रही हैं, आगे क्या होंगे इन टेक्नोलॉजीज़ की आने वाले सालों में। उसमें से हमने डाटा यूज़ किया था, और उसमें अजम्पशंस यही थी जो हम नॉर्मली ले रहे हैं अपने स्टडीज़ में भी, कि बैटरी चार्जिंग डिस्चार्जिंग एक ही साइकिल ले रही है 24 आवर्स में, कि जब 4-6 घंटे ऐसे मिले जब बाहर सबसे कम प्राइस है तब चार्जिंग आप कर लें, और जब हाई प्राइस आ रही है तो तब 2-4 घंटों में उसको आप डिस्चार्ज कर दें। तो ये सारी वैल्यूज़ जो हैं कॉस्ट की वहाँ से ली गई हैं उस रिपोर्ट से। तो ये वैल्यूज़ रिप्रेजेंटेटिव हैं, हर टेक्नोलॉजी के लिए ये ली गई हैं। और एनी अदर क्वेश्चन प्लीज?
थैंक यू डॉक्टर साहब, वेरी नाइस टॉक। सो मुझे असल में 2 क्लैरिफिकेशन से क्वेश्चन है। एक तो ये कि आपने जो लाइफ टाइम लेट्स से 15 ईयर्स के ऊपर आपने इसको कैलकुलेट किया ओवरऑल?
जी, हमने एक ऐसा ईयर फाइंड आउट किया जिसमें सारी जो है वो उनके मल्टीपल आइट्रेशन आ जाए, मतलब मल्टीपल रिप्लेसमेंट्स के बाद, जैसे ये सबसे ज़्यादा रिप्लेस होगी लेड एसिड बैटरी है, तो इसको हमने 8 लिया, ये इसका नंबर ऑफ रिप्लेसमेंट्स हैं, और आप इसको 2 ईयर्स में ऑलमोस्ट रिप्लेस करनी पड़ रही है, तो 8 × 2 16, तो रफली 16 ईयर्स का पीरियड हम देख रहे हैं।
राइट, 16 ईयर्स के
जी,
पीरियड
जिसमें आपको ये रिप्लेस नहीं करनी पड़ेगी, ये 16 ईयर्स इसकी लाइफ है, जीरो रिप्लेस।
सो इसमें ना एक इनहेरेंट अजम्पशन है, वो इनहेरेंट अजम्पशन ये है कि बैटरी इज नॉट इंप्रूविंग फ्रॉम डे 1 टू डे लेट्स से 16 ईयर्स, वो कांस्टेंट है, वो एक ही बैटरी है, एक ही तरह की है, और उसमें जो लेट्स से बैटरी की इंप्रूवमेंट होती है ओवर द लाइट से एवरी ईयर या एवरी 3 ईयर, राइट? तो वो आपने कंसिडर किया इसमें
बैटरी की इंप्रूवमेंट या डिग्रेडेशन?
इन टेक्नोलॉजी?
अच्छा, in technology.
लेट्स से आप रिप्लेस करते हो, आप एग्जैक्टली वही रिप्लेस तो नहीं करते ना, आप बेसिकली आप कुछ
सही है,
रिप्लेस करेंगे ना।
असल में देखें, जब हम इन्वेस्ट करने लगे हैं उस वक्त तो हम देखेंगे कि इस वक्त कौन सी बैटरीज हैं जो कि मार्केट रेडी हैं, जो अवेलेबल हैं, क्योंकि आपको पता है कि बहुत सी बैटरीज हैं जो शायद डिस्ट्रीब्यूशन ग्रिड में लग जाए या स्मार्ट ग्रिड या माइक्रो ग्रिड में लग जाए, लेकिन जहाँ तक हाई वोल्टेज सिस्टम है, ट्रांसमिशन सिस्टम है, तो वहाँ पे ज़्यादातर लिथियम आयन अब लगना शुरू हुई हैं, और लिथियम आयन मेनली लग रही हैं, यानी उसमें बहुत कम टेक्नोलॉजीज हैं। तो जो क्योंकि ये जो रिपोर्ट है बाय नेशनल रिन्यूएबल एनर्जी लैब है, तो इसमें हमने ये किया है कि उन्होंने जो उनके पास मार्केट का ट्रेंड है वो अवेलेबल है, और जो उनके पास रिसर्च के ट्रेंड्स हैं वो भी अवेलेबल हैं, तो उसके बेस पे वो ये कह रहे हैं कि ये 4 बैटरी टाइप्स जो हैं ये हम इनके ये डाटा दे रहे हैं, क्योंकि हमें ये एंटिसिपेशन है कि ये यूज़ हो सकती है, ये यूजेबल है, ये फिजिबल है डिप्लॉय करनी, तो उसी पॉइंट ऑफ व्यू से हमने इन्हीं तक फोकस किया, इन्हीं 4 टाइप्स पे रहे हैं।
Right. No, so I'm not questioning the types. I'm questioning the improvement in the technology over time. So I'm assuming that there is no improvement in 16 years. Is something different than assuming that we have a gradual, let's say, 3-year or 4-year improvement over time.
आप सही कह रहे हैं। अगर अभी तो हमें नहीं पता कि इम्प्रूवमेंट होगी या नहीं, अभी हम इन्वेस्ट करने लगे हैं, अगर हम इसमें इन्वेस्ट कर देते हैं, इन्वेस्टर के पॉइंट ऑफ व्यू से देखें तो वो 15 ईयर्स तक तो अब उसकी बैटरी जो है वो चल रही है ना, मतलब उसमें वो डेड नहीं हुई, या वो बल्कि ऑल्दो उसकी डिग्रेडेशन तो आएगी जाहिर है, लेकिन वो चल रही होगी। तो एट दिस पॉइंट अगर उसने चूज करना हो कि मैं किस लोकेशन पे इन्वेस्ट करूं क्योंकि मुझे पैसे बनाने हैं, उसके पास पैसे पड़े हुए हैं, तो वो तो फिर यही देखेगा कि कौन सी टाइप्स हैं जो कि, और उनमें से इस वक्त मैं क्या कर सकता हूँ। आपकी बात ठीक है, ये तो ऑलवेज होता है कि आप एक टेक्नोलॉजी में जो इस वक्त करंट टेक्नोलॉजी अवेलेबल है, जैसे पीवी की भी है, तो जो भी इन्वेस्टर है वो अच्छी से अच्छी टेक्नोलॉजी आज लगाता है, लेकिन वो 2 साल बाद तो वो टेक्नोलॉजी जो है वो अगली आ चुकी है मार्केट में, बट नाउ दे आर स्टक विद दैट टेक्नोलॉजी, दे कैन नॉट डू मच अबाउट इट। ठीक है, सो दैट्स हाउ इट इज। इसमें भी हमने ये एज्यूम किया है कि इस वक्त जो अवेलेबल है हम उसी की बेस पे चल रहे हैं, और हाउ इट इज।
So the second question is कि जो हमारा बिजनेस मॉडल है वो उसको ज़रा देख लेते हैं व्हाट यू आर सेइंग इज कि मेरे पी कार में चार्जिंग करनी है और उसके बाद मुझे डिस्चार्जिंग करनी है, तो ये इट्स रफली स्टैंड्स टू लाइक 6 to 8 hours
जी
तो बाकी टाइम पे ये नहीं कहना ये बेसिकली आइडल बिजनेस है, राइट?
ठीक ठीक
ऐसे ही है।
ऐसे ही है। असल में ये ना कि इसमें डेल्टा एलएमपी या लोकेशनल मार्जिनल प्राइस में जो डिफरेंस है वो बहुत हाई होता है बहुत सी जगहों पे। हमारे यहाँ तो जाहिर है कि हम वी हैव अ स्टडी प्राइस यानी कि यूनिफॉर्म प्राइस है, या फिर हमारे पास 2 रेट टैरिफ भी है। अब 2 रेट टैरिफ जो पाकिस्तान में है भी 3 फेज मीटर्स पे, उसको आप देखें तो हमारी पीक रात 1 बजे आ रही है समर में बहुत से दिनों में, जबकि हमारे पीक आज जो शाम को है। सो दैट इज नॉट इफेक्टिव इधर, दैट प्राइसिंग मैकेनिज्म इज नॉट इफेक्टिव। सो हम दूसरी रिसर्च में ये प्रपोज कर रहे हैं कि पाकिस्तान के लोड प्रोफाइल को देखते हुए कौन सा प्राइसिंग मैकेनिज्म जो है पाकिस्तान में ज़्यादा बेहतर है। तो यूएस में या दूसरी मार्केट्स में बहुत ज़्यादा प्राइस की वेरिएशन आती है, तो वो इवन डूइंग बिजनेस इन दोज 4 आवर्स कि उसमें चार्ज कर लिया उसमें डिस्चार्ज कर लिया, उससे उनको इनफ डेल्टा एलएमपी मिल जाता है, इनफ उसमें उनको मिल जाता है कि दे डोंट नीड टू ऑपरेट थ्रू आउट 24 आवर्स।
एंड विदाउट कैपेसिटी चार्जिंग,
विदाउट मतलब इसमें हम कैपेसिटी चार्जेस को तो कंसिडर नहीं कर रहे हैं, क्योंकि मेनली स्टडी जो है रिलायबिलिटी टेस्ट सिस्टम पे किया है, तो यूएस के मार्केट के पॉइंट ऑफ व्यू से लोकेशनल मार्जिनल प्राइसिंग सिस्टम पे किया है। तो इसमें तो ये होता है ना कि एवरीबॉडी कम्स इन द मार्केट विद देयर ओन रिस्क, देयर आर नो गारंटीड टैरिफ्स, देयर आर नो कैपेसिटी चार्जेस। सो हर इन्वेस्टर अपनी रिस्क लेके इन्वेस्ट कर रहा होता है, तो कैपेसिटी चार्जेस का तो वो पहले से स्टडीज कर सकते हैं। हम इस पे आकर स्टडी कर रहे हैं कि कैसे आपके पास अगर एनर्जी प्राइसेस का डाटा हो हिस्टोरिकल, तो आप उस पर मशीन लर्निंग टेक्निक्स लगा के फ्यूचर प्राइसेस फोरकास्ट करें, और फ्यूचर प्राइसेस फोरकास्ट करते हुए आप देखें कि कौन सी लोकेशन ऑप्टिमल हो सकती हैं, कहाँ आपको मैक्सिमम डेल्टा एलएमपी फॉर एग्जांपल मिल सकता है, कहाँ इन्वेस्ट करना बेहतर है। तो इन्वेस्टमेंट की जो लोकेशन है वो मल्टीपल वेज में आप डिटरमिन कर सकते हैं। सिस्टम ऑपरेटर के पॉइंट ऑफ व्यू से अलग हो सकती हैं, और आपके जो प्राइवेट इन्वेस्टर उसके पॉइंट ऑफ व्यू से डिफरेंट हो सकती हैं। और ऐसा भी हो सकता है कि दोनों की जो लिस्ट हैं वो आपस में कहीं मर्ज कर रही हैं, कोई ऐसी लोकेशंस हो जो सिस्टम ऑपरेटर के पॉइंट ऑफ व्यू से भी बेस्ट है, क्योंकि वहाँ पे लॉसेस कम हो रहे हैं, रिलायबिलिटी इंप्रूव हो रही है, और प्राइवेट इन्वेस्टर को भी वहाँ बहुत फायदा हो रहा है। तो वहाँ पे आप प्राइवेट इन्वेस्टर को फॉर एग्जांपल बेनिफिट दे सकते हैं, सोशल कॉर्पोरेट रिस्पॉन्सिबिलिटी के क्रेडिट्स दे सकते हैं कि आप यहाँ इन्वेस्ट कर लें, आपको फायदा तो होगा ही, साथ में जो कि कंट्री को फायदा हो रहा है, तो आपको हम सोशल कॉर्पोरेट रिस्पॉन्सिबिलिटी पूरी करने के क्रेडिट्स भी दे सकते हैं, समथिंग लाइक दैट। एनी अदर क्वेश्चन प्लीज? यस,
लेट्स थैंक आवर स्पीकर।
थैंक यू वेरी मच।
Thank you, sir, for your informative talk. Now we would like to invite Dr. Amir Mahmood to present the senior to Dr. Kashif Imran. Camera. Our third invited talk is PV Policy of Pakistan and Industries in Cooperative Debt Policy by Professor Dr. Tahir Izhar. Professor Dr. Tahir Izhar is an alumnus of UET Lahore. His session at UET Lahore was year 1978 at the Department of Electrical Engineering. Dr. Tahir did his MSc in Electrical Engineering from UET Lahore and got his PhD in Electrical Engineering from University of Birmingham, UK. He is also attained an MBA degree from Institute of Business and Management of UET Lahore. He served as a very prominent faculty member at the Department of Electrical Engineering, UET Lahore, for almost 35 years. He worked at several administrative posts at the university as well. He remained chairman of the Department of Electrical Engineering at UET Lahore and served as Dean of Electrical Engineering faculty as well. He has been actively involved in research, training, teaching, and consultancy for the last 38 years. He is an expert in andragogical training for in-corporate sector to implement energy management in their organizations. He also served as a consultant GISWICWA GmbH for developing teaching and learning materials for energy efficiency advisor courses. He is also a certified trainer and evaluation for competency-based training for NVTech. Currently, he is heading R&D team at Maxwell Power Private Limited for their ongoing project related to solar energy systems. Dr. Tahir remained a very active researcher during his professional career and published 57 international research papers. He supervised 4 PhDs, 49 MPhils, and 80 BSc engineering final year project design. Please, sir.
Thank you very much for a very nice introduction. So the topic of my talk today is solar PV module and allied equipment manufacturing policy by the government. First of all, this is the presentation outline. I'll first introduce my company, Maxwell Power Private Limited, and then I'll discuss Pakistan solar energy scenario and future trends, role of government bodies, importance of government policies for sustainable growth, government policy and solar energy products, then key recommendation, and finally the conclusion. Maxwell Power Private Limited started solar-related business in 2012, just about 12 years ago, with one shop office at Hall Road, Lahore, with a great vision. I joined this company in 2020 after retirement from UET Lahore, and my commitment was to take the company to a height where we can produce all major solar equipment, including solar panels, modules, and inverters, design indigenous local inverters, and batteries. At that time, only one engineer in a small repair and maintenance shop at Hall Road was working. Now, in 2024, we have more than 100 engineers working in Maxwell Power in our module manufacturing factory in Raiwind, maintenance center all over Pakistan. We have maintenance centers for our range of inverters in all over Pakistan, in Peshawar, Islamabad, Karachi, Sakhar, Hyderabad, Multan, all over Pakistan. And we have a main maintenance center at our head office in near Gulshan Ravi, Band Road, and all our offices are there, and we're maintaining all of our equipment over there. And I'm also heading R&D department, where we have 5 engineers at the moment, and we're looking forward to increase the number of engineers in coming future so that we can produce all our equipment locally. Our great vision to be the biggest stakeholder in the national access to clean electricity on a large scale, a clean and environmentally stable Pakistan where renewable energy constitutes a major part in the energy mix. Our product lines. Presently, we are producing solar modules in our manufacturing plant. At the moment, we have the state-of-the-art latest plant, but with a very small production. That's only 20 megawatts per year. Energy export control and monitoring devices. We have indigenously developed these products to control and monitor the energy flow when we connect the solar systems. Solar VFDs, for solar tubes. And solar batteries, we are dealing in solar batteries as well, on-grid solar inverters, off-grid solar inverters, and hybrid type of solar inverters. So these are our product range. This is the layout of our 20 megawatt manufacturing plant. So this is the Ecoprogetti company of Italy, and it is the latest plant. We have chose semi-automatic plant, not the fully automatic, so that we can control the quality. They are suggesting six operators per shift, but we have more than six operators and about 5 engineers, so that we can control the quality and make our modules best in the world. So in our factory, we can produce all type of panels. I mean, the double glass, bifacial, half cut, 3 cut, with any number of bus bars, any size. And the purpose of this is that we can produce these panels according to our required market, the niche market. Why manufacturing in Pakistan? First thing is the quality. So quality control is now in our hands. We can select the best raw material. We can test the materials in our laboratories. We have all the best high quality test equipment imported from Italy to test all the input materials so that the output quality is best. Filling the niche. There are certain markets in which we, if you want to install a panel on your rooftop, and about 5 years ago, the maximum panel size was only 300 watt. And now you cannot find any panel less than 500 watt. Or even they are getting, the power is getting more and more. And now we are listening about 580 watt. Why they are increasing the power of the panel? It's not the size. The size is also increasing. So they want to reduce the cost on the compromise of the quality. So when we have a bigger size in the panel, it is difficult to handle. On the rooftop, the glass is thinner, frame is also thinner, and the physical strength of the panel will be small. We're using 3.2 millimeter thickness of glass, while the imported panels are using 1.8 millimeter glass thickness. They are reducing the weight and size of the frame, glass, and all other materials to reduce the cost. Reduce price. Okay, when we produce all these equipment locally, you can have a lesser price, obviously. Job opportunities, that is the main goal of our company, that we can increase the availability of jobs for our young generation. Local raw material production. So when you're producing all these equipment locally, then it's a vertical integration. Initially, you import all the equipment from outside, and when the production capacity increases and the quality, you can get the improved local quality from the local market, you will prefer to use local materials. But there will be no compromise on the quality. We have all the international test certification for the raw material as well. We have to test all the raw materials in our factory and in the national laboratories as well, accredited by PNAC. And finally, the export opportunities. Now, you can have heard about the restrictions imposed on China to export their materials and products to Europe and USA. So there's a big opportunities there. If you have all the facilities, high quality facilities available to manufacture the solar equipment in Pakistan, you can import the raw materials from any European country and you can export them to Europe and the USA. The huge scope of solar business in Pakistan. 5 gigawatt of solar PV modules imported in the last 5 years. At the moment, there is no tax on the import of any solar modules, solar panels, and on-grid solar equipment. There is no sale tax, no tax at all. So the increase is there, but still, I will show you that the total share of solar power is very small. 700 megawatt solar equipment imported in just 2016 in 1 year. 2.4 gigawatt solar equipment imported in 2021. So you can see the growth of the solar systems, the import of the solar equipment is increasing. Demand is increasing at the rate of 50%, expected to be 12 gigawatt in 2025. Less than 2,000 megawatt in grid connected. So this is the point here that the grid connected power is only 2,000 megawatt with a total generation capacity of more than 40,000 megawatt. This is the graph showing the solar PV global capacity. And you can see that it is exponentially increasing. And you can see the share of India, Germany, Japan, and China. The growth of China is maximum. That is why they are producing more cheaper equipment, solar equipment. Just last year, they have reduced the cost to 50%. So the import price, FOB Karachi was last year it was 21 cent, and now it's only 11 cent. So reduced to nearly half. And that is the mega scale production. They are increasing their production to reduce the cost. So cost will only decrease when you increase the capacity of your production. This is the share of electricity generated by the renewable energy of the top 10 countries. And you can see that solar is getting more share. Day by day, wind is also there, but in Pakistan we have the opportunity of solar is much more and it's much cheaper as compared to wind. Job growth. So you can see that additional jobs from 2018 to 2050 will be 15.5 million. So this industry is growing a very fast scale, as I've shown. I have told you about my company, just from 1 engineer to more than 200 engineers in just 4 years. So technically, jobs are increasing. And all the universities are producing the technical people, and this industry is promising more jobs as compared to other process industry. This is basically the manufacturing of solar PV modules. So 6 main components which are used to manufacture the solar module. First important thing is the solar photovoltaic cell. And then the tempered glass, which is a special solar glass, because in normal glass, what we have, the capability of the glass is that we have more iron contents there, and it is tinted, and we want to reflect the ultraviolet light, and the transmittancy of the glass is less. But this solar glass needs all the light to pass through the glass, even the ultraviolet light as well, because all the light spectrum is producing power. Then we have the glass, and we are using 3 to 3.5 millimeter thick glass, imported from best producers in the world. Extruded aluminum frame, and you can see in this diagram this is the frame, this is the glass, and we have the encapsulating sheets. It's called EVA, ethyl vinyl acetate, and the melting temperature of this sheet is just 180 to 100 degrees centigrade. So we pack this with the, we place the cell basically on the glass, and then place these EVA sheets on the top and bottom of the cell, and then put it into the lamination machine, where the temperature is about 150 degree, and keep it for 15 minutes in that machine, and then it is laminated. And now it is safe to be operated outdoor with all hailing and rain, under the rain, for about more than 30 years. Then we have a polymer rare backsheet. It's maybe opaque or transparent, or we can have another glass down there for bifacial panels. And then we have the junction box with diodes and connectors and leads. This is the manufacturing process. First of all, the glass is laid down on the layup station. So, and then the cells are loaded in the Tabor stringer. Tabor stringer, this is Tabor stringer, layup station and Tabor stringer. Tabor stringer will make strings. The connections are on the top of the cell and on the bottom of the cell. This is the standard N-type or P-type cell. In P-type cell, the negative is on the top, and in N-type cell, the positive terminal of the cell is on the top. So we connect all these cells in series, and then we have to bring the external terminals through the junction box. So the Tabor stringer will make the strings, and then strings will be connected together using this busing system. This is the busing, and then we have to test the connections through electroluminescence testers, and then finally the lamination. After lamination, the panel is ready now, and now we have trimming of the extra plastics, and then framing, and then junction box, and finally the module is tested on sun simulator and high potential test, and again EL test, and that's all. The EVA and backsheet cutter is off the line. So you can see in bottom there, this is off the line, and this is the line. So production is in a line. The important performance of the panel is its degradation due to the induced potential and induced light. PID is induced degradation of the panel because of the potential, and there may be a failure. So this graph basically shows the degradation because of this. Cell technology roadmap. Cell is continuously improving. Earlier in 2018 and 19, we have polycrystalline cells, And then in 20s, monopoly perk was introduced. In 21 to 22, mono perk, P-type perk and N-type was introduced. And now we have IBC and TopCon technology, and in future we will have HJT technology. And the most of the share in 27 will be HJT type, which have more efficiency and more life. This is just comparison of a P-type and N-type cell module made by the P-type and N-type cell. This red shows the P-type, which is the older technology, and new technologies N-type. You can see that this can sustain up to 30 years with very small loss in the output. So the test is actually the loss of the output. It should be less than, in the first year it is about 2%, and beyond that, after 30 years, the reduction should not be more than 15%. Batteries are also very important. At the moment, lithium iron phosphate batteries are being used. We are also assembling these batteries in Pakistan, and the cost of the battery is about $300 per kilowatt hour. Sorry, it's about 3 lakhs per 5 kilowatt hour battery. That is our selling price. And we are offering 6,000 cycles, warranty for 6,000 cycles, and that is about 10 years with 80% DOD. And if you decrease the DOD to 60%, the cycle life will be more than 10,000. And another battery which is coming in future, and we are working on that, and we are going to assemble those batteries as well in Pakistan, that is the sodium-ion battery. The weight and volume of the sodium-ion battery is much bigger than lithium iron phosphate, but the cycle life and the cost of the battery is much less. The biggest company in China, CATL, is promising that in 2025, the per unit cost, that is 1 kilowatt hour cost of the battery, will be only $40. So at the moment, the lithium iron phosphate is giving us about 12 rupees per kilowatt hour storage cost. And with that sodium ion battery, it will be less than 5 rupees per unit cost. So the cost of the solar, if you work it on the total capital cost we are investing on the solar equipment for 30 years, the cost of the per unit solar is only less than 3 rupees. Or 3 rupees plus 5 rupees is 8 rupees. So 8 rupees is that if you store your own electricity and use it during the night. So in near future, we're going to say goodbye to net metering, and we're using these batteries for the storage of our own electricity. The role of government bodies in electric power. This is the list of government bodies. GENCOs and IPPs, they're responsible for producing the power. Earlier we have GENCOs, the generation companies like Tarbela, Mangala, Kotaddu and others. They are operated by the governments. But in early 90s, it was decided that it is more expensive to generate power through government. We should privatize it. So they have produced IPPs. They have introduced IPPs that onwards from 1993, I think, no company, government will not produce any power. Private companies will produce, and they will sell the power to NTDC. NTDC, National Transmission and Distribution Company. The WAPDA was broken into these companies so that in future they can be autonomized and they can be privatized. NTDC will buy the power, electric power from GENCOs and IPPs, and distribute it to the DISCOs. DISCOs is distribution companies. There are at the moment 10 distribution companies in Pakistan, including LESCO in Lahore. Then we have NEPRA. NEPRA is the regulatory body. It will set the prices, and it will control the IPPs, NTDCs, and any disputes in DISCOs, NTDC, or DISCOs in IPPs and NTDCs and all that. So NEPRA is actual government body to regulate the all the power system. So NEPRA is very important, and in future only NEPRA will be the government bodies, but all the other will be privatized. Then we have PNAC. PNAC is National Accreditation Council. It accredited the laboratories in Pakistan so that the equipment produced in Pakistan should be tested according to international standards so that the buyer should have confidence on the equipment, what they are purchasing. Then we have AEDB, Alternate Energy Development Board. It is to develop and facilitate the alternate energy systems in Pakistan. Then we have EDB under the Ministry of Industries, Engineering Development Board. This is the government body to prepare policies related to the new technologies in the country. And they make all these policies, and these policies are vetted by the Ministry of Industries and approved. Then we have energy departments, PEPCO, for example, and energy departments, Punjab Energy Department and the Federal Energy Department. They are actually giving the policies and the funding for the development of the products and facilities for the energy. ICECE, Indicative Generation Capacity of Electric Power. This is the report prepared by NTDC every year and give 10-year planning for and submit this report to NEPRA. So the purpose of this is to identify new generation requirements with capacity fuel technology. And they make all the business plans, they calculate the cost and everything, and then prepare a report and submit to NEPRA. Safety, the loss of load probability, not more than 1%, it have to satisfy that. Cater for the long-term load growth forecast. So forecasting is also the responsibility of the NTDC, and it will prepare this report and give all the requirement and the forecast and calculations. They have all computer centers in Lahore, the latest computer available, and the software, latest softwares, and they actually run all these models on the computer and then give the forecast. Provide at least the cost optimal generation expansion plan. This is a graph taken from ICECE 2022. That is the latest report submitted in in the end of 22, and it indicates the generation capacity and load forecast for 22 to 31 for 10 years. So the blue line shows the GDP growth of Pakistan, and the sale of electricity is shown by the red line. So you can see that the growth and sale go hand by hand. So if you want to increase the GDP growth of Pakistan, say 6%, for example, then the growth of generation should also be 6%. So 6% electric growth means that in 12 years you have to double your capacity. So if you have 40,000 megawatt now, after 12 years, you should have 80,000 megawatt of electricity, which is required. This graph is also taken from the ICECE, anti-DC system annual energy generation. So you can see the share of renewable, which is only 4%. And thermal is very high, 58%. Nuclear is also increasing, 13%, and hydro is 25% only. This is the percentage mix of category-wise sale in gigawatt hour of electricity. So you can see that the industry is only 27%, which is alarming, and domestic is using 49%, which is, I think, highest in the world, share of the domestic use of electricity. Let's now discuss the salient features of the government policies on solar energy products, draft prepared by EDB after consultation with all the stakeholders. They're preparing this draft for the last 6-8 months, and they have taken on board all the stakeholders from the Trade and Chamber Commerce, chambers of all Pakistan and the industries which are producing solar products, traders, and the Solar Association of Pakistan. All the representatives are there, and they participated in the preparation of this draft. Policy vision: to make Pakistan a regional hub for manufacturing solar panels and allied equipment, to facilitate investors for solar panel manufacturing, to serve domestic as well as export market, US, EU, and other market, to achieve 100% value addition by setting up manufacturing ecosystem. Silica mining, crystal silicon ingot formation, solar vapor, solar cells, solar panel parts like tempered glass, EVA film, aluminum frame, cabling, junction box, etc. Inverters and storage systems, that is the solar batteries. The comparison of the solar, the cost of the, in a solar system, the PV module is, the cost of the PV modules is 45%. So the maximum is the PV modules. Solar potential. This slide shows you the solar potential in Pakistan. So you can see that 32,000 megawatt by 2031. This is the vision of the ICECE. Solar power generation share 10,000 megawatt by 2031. So they want to solarize government buildings, and electric diesel tube wells should be solarized. Current solar share on connected to the grid is only 600 megawatt. Import in last 5 years is 5,000 megawatt, and annual to be added is 1,250 megawatt on grid. So annually we have to increase this, and then 50% increase every year. There's a need to create a domestic industry to fulfill local demand for solar equipment, soaring global demand for solar equipment. Pakistan may become one of the top 20 global market with rising total demand from utility projects on grid and off grid. Export potential is $20 billion per year from this industry. This is an estimate for the plant, PV solar power plant, and you can see the machinery, land, infrastructure, engineers required, skilled labor, and unskilled workers, total job multiplier, so on. So this is the actually glass technology. You can see that the regular glass is greenish, but the solar glass is very clear. And this is the chemistry of the solar glass. In our local glass manufacturing plants, the contents of iron is much more, and it has to be decreased in solar glass. So additional plant is required to reduce the contents of iron. That is the main issue of the glass. So these are the component: tempered glass, inverters, and lithium-ion batteries, and their cost. Intervention required by the government: consistent 10-year policy framework. At least the policy should prevail for 10 years so that the industry can invest without any fear. Exemption from duty and taxes on import of plant, machinery, equipment. Exemption from duties of taxes on import of inputs used in manufacturing of solar panels initially. Okay. Inclusion of solar equipment, 10 years tax holiday for existing system, government procurement. Projects may have at least 20% share of local panels, increase in the State Bank of Pakistan financing, and so on. So these are the intervention required by the government. So already shown you the solar energy scenario of Pakistan. Testing facilities, this is also very important. Quality is ensured while the international standards, IECE standards. For PV, it's IEC 61215 and IEC 61730. Testing facilities. Presently, no testing lab is available in IEC standards. Center for Energy Research and Development, CERAD at UT Lahore, is doing few PV module testing, and they will become the future lab for testing, providing the test facilities for the solar equipment. Production test facilities are available at manufacturing from premises. PCRET with support of COITA Korea will have international accredited lab by 23-24. Target plans. So this is the year one: local assembly, industry, road ramp up, frame, junction, box, cabling, bus bar produce, and packing will be produced in next year. Tempered glass and EVA will in third year. Conversion from polysilicon to ingot to solar wafer in fourth year, and solar cell after 5 years. This is the policy of the proposed policy for indigenization. So initially the assembling will be done, and later on the equipment, the raw material will be added year by year so that they will be produced locally. This is the localization roadmap for AC/DC inverters. Policy localization roadmap for the storage batteries. Key recommendation: the creation of separate HS codes for solar PV modules and solar PV cells, removal of ACD and RD on the import of input required for manufacturing or assembling of solar panels and allied equipments, removal of CD, ACD, RD, GST, AST on import of solar PV manufacturing machinery, production line and equipment, gradual increase of custom duty, regulatory duty on import of finished goods, removal of sale tax on import of input, treating local manufacturing of solar panels and allied equipment as green energy equipment, phase-wise localization of parts, components and imposed duty as per the localization plan. Conclusions. PV-based energy systems are cheapest source of energy in Pakistan. PV module life is more than 30 years now and capable of providing 80% of power even after 30 years. Very low maintenance cost, only available during daytime. That is the main problem. Expensive for off-grid systems. Power system stability issue with increasing PV-based loads. Station storage batteries can be used for system stability. Charging stations for EV can also be used for system stability. Numerous benefits for local manufacturing of solar PV equipment. Thank you. Any questions? You're most welcome.
Thank you very much, Dr. Saab. It's very, this is the need of requirement right now. This solar panels and everything is to be done. But I'm not sure about the MAPCO or LESCO policy, for example. These companies, what they will be doing, they are changing the policies with respect to the Pakistan requirement or whatsoever. So are they helping the people to have a more solar system in the market? Thank you.
Very good question. A very good question. Thank you, Dr. Kamran, for sparing your time and coming here. He's Vice Chancellor, Nawaz Sharif University. The everybody, government bodies working very hard to promote solar energy in Pakistan. So there are rumors there that the cost of electricity which they are purchasing is less. At the moment, they are purchasing at a very high rate. That is about 22 rupees per unit. And they are giving you, in return, the same units, which you export, same unit in the night. Though you know that they are buying at very high rate, but still they are giving you, and your production is only for peak hour is only 5 to 6 hours only during 24 hours. But they are giving you the electricity for the whole time. And the payback period is less than 2 years. So which business is that? All the equipment is on your roof, and for example, you invest 1 million rupees for about 10 kilowatt system, and it is generating 15,000 kilowatt hour, 15,000 units per year. So if you just say the cost of the electric unit is 50 rupees, so you're using it for yourself, then the payback period is less than 2 years. So there's no business in Pakistan which can give you so much high return and all your investment on your rooftop. So these are just rumors, and they have all the standards. If you install the IPP, for example, a solar system connected to grid just to sell the power to the grid, the rate is only 15 rupees. But for rooftop, domestic solars and industries, they are paying 22 rupees per watt. And in return, they are giving the unit back to you in the evening. So that is not available throughout the world. Any other question? Thank you very much for your patience.
Thank you, Professor Dr. Tahir Ishar, for your informative talk. Our fourth invited talk is Energy Management in Microgrids, Exploring Methods, Solutions, Challenges, and Prospects by Professor Dr. Mohammed Benbouzid from University of Brest, France. Dr. Mohammed Benbouzid completed his PhD in electrical at the National Polytechnic Institute of Grenoble in 1994. He furthered earned his habilitation a de rigueur dis recherche degree from the University of Amiens, France in 2000. Following the completion of his PhD, Dr. Benbouzid joined the University of Amiens, where he held the position of Associate Professor in Electrical Engineering. Since September 2004, he has been affiliated with the University of Brest, France, where he currently serves as a full professor in electrical engineering. Additionally, he holds the distinguished positions of a distinguished professor and a 1,000 talent expert at the Shanghai Maritime University in Shanghai, China. Professor Dr. Mohammed Benbouzid's primary research interest and expertise include control to electrical machines, variable speed drives for traction, propulsion, and renewable energy applications, and fault diagnosis of electrical machines. Professor Dr. Mohammed Benbouzid is an IEEE Fellow and a Fellow of the IET. He is the Editor-in-Chief of the International Journal of Energy Conservation and the Applied Sciences MDPI section on electrical, electronic, and communication engineering. He is a subject editor for the IET Renewable Power Generation. He is joining us on Zoom today. Please welcome Professor Dr. Mohammed Benbouzid with a big round of applause.
Okay, so I think I can start. Okay, I would like to thank you for this kind introduction, and I would like also to thank the organizer for the invitation. And I will proceed with my speech and my presentation. And this keynote is entitled "Energy Management in Microgrids." I will try to introduce you methods and solutions, and I will focus at the end on challenges and prospects. So, this should be the outline of my presentation. So I will start by. I hope the sound is okay from your side. Okay, so the outline of my presentation should be first maybe an introduction just to introduce the context. Typically, why renewable energy, that later be the main component of microgrid. Then I will try to give some definitions about microgrid, followed by defining an EMS and energy management systems for microgrid, and I will finish this presentation by some prospects and the challenges. Okay, so I will try to answer quickly why renewable energy sources. So in this first slide, just to highlight, of course, the need for moving from fossil fuel to renewables because of, as indicated here in this slide, we have some data. Even these data are changing. But the trend is here. Okay, we have some historical progress related to the CO2 emissions. You can see that there is a clear need for renewable energy sources. We can see that we are targeting, of course, to minimize this emission, and you can see the trend in 2030 and 2050 from 25 gigatons to 9.5 gigatons, and this is only possible if we make the expected transition from fossil fuel to renewables. So if you can see in the last line of this slide, you can see that there is a slight change in fossil fuel demand compared to, for example, the reference year is 2016. There is a clear change, and the expectation in 2015 are huge, because we expect, for example, to decrease the oil demand by 70%. Still addressing this question, why renewable energy sources. So here I'm highlighting the 5 technology pillars for the future of energy. These pillars will be later used as main components in a microgrid. So you have here some indicators in terms of renewable shares, and typically the expectation in the future. The target, this is data by IRENA here. You can see that by 2050 we're expecting 86% share. This is almost the case for some specific country like Denmark, where the grid is almost is close to 100% renewables. So you can see also here that the electricity share of final energy as a target in 2015 is 48%, and this could be possible only by using renewable energy sources. In terms of technologies here, some additional items, and this is the case. Actually, there is a huge development in electric, maybe first hybrid, then electric cars. So this component, these technologies, I mean here electric cars will be later used as maybe one additional component when managing energy in a microgrid. So still addressing the question of why renewable energy sources, and maybe now starting to focus on the main on the microgrids. So and this is typically the case of my region here in the west of France. Yes, sometimes there is an availability of energy supply for some region, and this is the case for some remote areas, typically island. Here in the Bretagne region, called Brittany here, we have so many islands. Actually, these islands are using fuel as the base for electricity generation, and the target is in 2030 is moving from fuel to fully renewable energy sources. And for this typical place, I mean here island, the challenges when supplying these islands is how to manage the load and renewables variability. You can see here in this illustration, there is, of course, one of the main maybe disadvantages of renewable sources is the fluctuations, and we need to manage these fluctuations regarding the load requirement. We'll see this later, that this will be, if you want to move to 100% renewable energy sources, we need to introduce a key technology, which is storage. Actually, these fluctuations in island, typically, I will show you an example of Western Island here in Britain. This fluctuation is managed using diesel unit. So this is what we want to progressively move on, is the generation mix. This is an illustration of an island in Greece, Crete Island. This is really a big island here in Greece. You can see that actually there is a mix using PV, using wind, and of course using fuel, classical generation, including gas, diesel, and steam units. And the target here in this island is to progressively move to full renewable energy sources to fit this island. The issue here is, of course, still how to manage the fluctuation of renewables and to cope it with the load management. So in terms of renewables installed capacity, you can see here. Maybe I will try to move to the 2020. Even here, that we can see that there is a sort of exponential evolution. We can see that there is, in terms of capacity, there is two main technologies here that are highlighted. The first one is the solar PV, and the second one is the one known is renewable hydropower. You can see in my slide here, you can see something that start emerging in 2005, which is marine renewable energy. And actually here, you can see in this picture here, actually in France and also in UK, we are trying to progressively introduce marine renewable energies, typically tidal stream turbines, as additional component in terms of renewable energy sources. So regarding this installed capacity, we can compare it to the trends in renewable in technologies. And of course here, two technologies are maybe considered as almost classical one: renewable hydropower. This is typically in France, we have a huge share in terms of hydropower. Sometimes we can consider as a renewable. It uses barrage and so on. Solar is also hugely developed, and actually in Europe, also in Asia, there is a huge development in terms of wind energy technologies. Okay, so maybe in this slide, just to highlight this technology trends, you can see here that typically hydro is a major technologies, but new technologies are becoming almost majors. Typically onshore wind, even if offshore wind is progressively being majors and actually is in deployment, massive deployment. So now I'm coming to the topic of the main topic of my presentation, which is microgrid. So in terms of definitions, there is different definitions, but I will come to the sense I'm giving here in red. Microgrids are typically defined by their function, not by their size. So sometimes we can make the mistakes to trying to compare power grid to microgrid in terms of size, but microgrids are definitely defined by their functions. We can have big microgrids, and we can have also small ones. Sometimes we use the term nanogrid. So typically, a microgrid is an integrated energy systems, and mainly constituted by distributed energy resources, like DR, and with multiple energy loads. So these loads can operate as a single controllable entity or in parallel. And this microgrid can be islanded from the existing power grid, can be connected or disconnected. So this microgrid is composed of localized load and generation resources. This resources, the target is that these resources should be renewables, and progressively moving from removing fuel-based resources and moving to renewables. And again, this microgrid can be disconnected from the main grid and operated as an island. As a conclusion, microgrid is small energy systems, and in this system we need to balance captive supply and demand resource, and with the objective, of course, to reach stability, but within a defined boundary. So this is an illustration. So a traditional power generation versus a microgrid. In a traditional power grid, we have, of course, generation, transmission, distribution, and consumption. And you can see here in this simple illustration. So in a microgrid, we have one main component, which is the microgrid central controller, and we will and there is an aggregation of course, resources. These resources can be typically conventional generation resources with the target to move to renewable energy resources. We have, of course, another important component, which is the energy storage systems, and some, depending of the microgrid localization, we can use also smart homes as an additional component. We can also use, depending on the development of the electric vehicle market, we can use also electric vehicles as a power source, but also we'll see later that as a storage source, as a storage system. So that maybe we need to answer the question about the need of microgrids. So this is first, and this was the point of my introduction. Maybe we introduced the problem CO2 emission. Maybe microgrids should be a solution of energy crisis by the uses of renewables, the storage also. It could be also a solution to the intermittent nature of renewable energy sources by an optimal management of these sources using storage systems. It is also reliable and continuous power supplies when the energy, the EMS, the energy management systems, is well designed. It's also solutions for local power generations. And of course, maybe last not least, it will address the critical issue of greenhouse gas emission control. Okay, so maybe following this answer to the question why microgrids, maybe the benefits clearly are high efficiency if we compare to conventional grid. This is thanks to an optimal energy management system using these microgrid central controllers. The benefits is that microgrids are designed to be located in proximity to the load. I prefer use are located close to the consumer. So in this case, when this is the case for microgrids, so of course we'll reduce transmission line losses compared to a classical power grid. So we reduce also the transmission and generation system outage according to the distance problem. And in this case, we can also, one of interesting benefits is the heat load integration for cogenerations. And of course, we have some ancillary services. So these are examples of well-known microgrids. So the first one is the San Diego Gas and Electric Borrego Spring microgrids. So you can see here the different components I have already introduced: distributed energy resources, the storage, and of course the microgrid controllers. I'm trying here to highlight the case of Ireland, because this is really specific to my region here, Western region in France, Bretagne. And here I'm highlighting two cases. The first one is one in Spain, and well-known one is the El Hierros island in Spain. Typically, this is 1% renewables. So we have here an island microgrid with renewables. So this, as you can see in this illustration, this island is using storage system, a very interesting storage system, and a huge capacity storage system. And typically, this is the pumped hydro systems. This is also the case for Western Island in France. Unfortunately, the Western Island in France, this is a well-known touristic island in Western France. This island is still using diesel generators to manage manage the power fluctuations, but the final objective is to remove this diesel generators. I would like to mention that this island is not connected to the main grid, so it is fully autonomous island. So the objective to remove the diesel generator is to use, as you can see here, these pumped hydro systems consisting in upper reservoir in the island. This is the reservoir, and the lower one should be the of course the sea. Okay, just to highlight the status of the microgrid markets, you can see even these data are around 2017. They are still maybe they are still informative. So even the report is a report of 2021. You can see that we have three different options: autonomous basic, autonomous full. I mean here microgrids and interconnected community. We can see that we have typically in terms of autonomic microgrids, we have major technology, major microgrids typically all around the world. In terms of full autonomous full microgrid, we have emerging. Even in some places, we have some major microgrids, typically in East and South Asia. And for the interconnected community, I mean, here's some cluster of microgrids. We have some pilot projects, and actually this is still limited. So, just to give a quick view about the revenue, microgrid revenue, we can see that this is an exponential increase in here, and this there is a great increased tendency typically in North America and in Asia Pacific, typically in China. Now, I will focus on the microgrid and with its component, their component typically, as already discussed, presented, distributed generations. Microgrid allows it to combine heat and power, and this is one of its benefit of microgrid. Another important component, maybe this is one of the main component, energy storage systems to manage the fluctuations. So we have also some metering infrastructures and smart meters. So this is typically, of course, to monitor the microgrid state, but not only the energy state, but also the health state. One possible plug-in electric vehicle and charging station. This is the case actually in microgrids in France and other places in Europe, and of course our smart appliances depending on the size of the microgrid. And of course, I should say last but not least, the EMS, the energy management systems that have with the main objective to manage all the listed component energy. So in a microgrid, we have different components. Typically, I would like to introduce one, and I will justify it later. This is the communication level, communication technologies. I will not spend much more time apart from showing you this slide. You can see the different technology we use in a microgrid, and maybe the communication label. This part will be later can be a sort of a door for cyber threat in a microgrid. So this is why later I will introduce one of the prospect or challenges for microgrid, which is cybersecurity. Okay, so in terms of classifications, microgrids can be classified in different types depending depending on the power type. Actually, we have AC, DC. Depending on the supervisory control, we can have some sort of decentralized or centralized microgrid. The operation mode, we have already seen that there is some islands, typically islanded mode and grid connected mode, depending on the number of phase and of course depending on the application. So this is a quick definition of an EMS. So an EMS is a process or a series of processes depending on the size of the microgrid that enables an organization to use data. So we start, of course, this is why I introduced the communication level, to use data and information to maintain and improve energy performance. This is mainly the main objective of an EMS is we want to target an optimal energy usage. So we optimize the energy usage while improving the operation efficiency of the systems. So in a microgrid energy management and operation, we have at least three levels. We have a tertiary level, secondary level, and primary one. For the tertiary level, in this level, we have the EMS. In this case, we try to optimize actions and reference, and typically we try to ensure energy at long terms. And in this tertiary level, the time range is from minutes to days. This is why this is an important level regarding an EMS. For the secondary levels, here we are managing the power. This is sometimes called the tactical level here, the secondary one, and we manage the power. We carry out voltage and frequency regulations that could be connected to what I mentioned previously as the ancillary services. And of course here, in terms of power management, we are carrying out sort of power sharing, and the time range is between second and minute. The last one is the primary level. We are here close to the controllers. We are close to the local controllers, and in this case, the time range is from microsecond to millisecond. So, just giving what are the challenges in microgrid management. So the first one is, of course, the modeling of the DER, the distributed energy sources. The second important challenge is the demand response integration. This is important regarding the microgrid constructions. And the last challenge is the flexible and adaptable design of microgrid EMS. I mean here the design of the EMS, not the microgrid. Regarding the process involved in an EMS, you can see here that of course we need to monitor data. Typically here, when we use renewable energy sources, we can monitor, we forecast for example, the irradiance, the wind speed, and so on. Of course, we can use also in a microgrid some classical power generation. So after collecting this data, we need to do some analytics, forecasting, and based on the data processing, we'll of course try to optimize the energy and this green level. This optimization can be related or can be connected to a sort of energy market. I will later talk about the transactive energy. And the last step here is close to the controller. This is real-time control, and this real-time control is connected to now not to the energy but to the ancillary market. So this is, I will try not to spend much time on this slide, but this slide is highlighting the two important parts of an EMS, which are the constraint and the objective. In terms of constraint, we have many type of constraint: energy balancing, demand response, reactive power support, reliability and so on, depending on the microgrid usage. In terms of objective, many type of objective can be related to the OEM cost of the energy storage system, maybe load shedding, penalty cost, loss cost, battery and I will try here. I will later highlight this battery degradation cost. Maybe I can say energy storage degradation cost, because this is really an important part to be considered within an EMS. So you have here these different type of objectives. Maybe I have not much so much time to detail it. But in terms of strategies, you have typically maybe three types. We have rule-based, we have classical optimization. This is almost, if you have a deep look on the literature, lot of work are done regarding this classical optimization, including linear programming, MIP, mixed integral linear programming, nonlinear programming, and so on. And we have, of course, dynamic programming that seems to cope more to the actual EMS. So we have also meta heuristics. I have listed here different type of meta heuristics, and what I can provide an advice maybe here in this meta heuristics. Seems that PSO or genetic algorithm are almost the most used and almost sufficient. No need to try to combine or to develop new meta heuristics, as PSO and GA seems to be efficient, and in addition, of course, to the classical technique. So in terms of artificial intelligence, now there is really a big tendency using specifically machine learning, and more specifically reinforcement learning based neural networks. This seems to be the great tendency regarding EMS. We have also maybe more classical one. Typically, I'll go till the end of my proposal, the model predictive control, and depends on the data analytics, and particularly the forecasting. If you have an optimal forecasting, we can adopt such kind of model predictive control. And last but not least, of course, in the literature, actually, we can see that there is sometimes researchers are mixing methods to optimize the EMS, and this is why I highlighting this hybrid methods. So this is just for illustration from a work we carried on microgrid EMS. You can see here in terms of objective function what we have considered as the main one, the PV cost, because here we are using DC microgrids, and typically for an island, the Western Island here in Brittany, and we are considering the PV cost, we are considering the battery cost, we are considering also the load shedding cost and the demand response cost. In terms of important things, we are considering an additional important cost is the degradation cost. This, I think, at this time, this is mandatory to be considered to consider the storage system. Actually, we are using for this island, we are targeting to use lithium-ion battery, so for storage as a base storage systems, and we need to consider the degradation cost within the EMS. So this is what we have done a sort of comparative study regarding the impact of this degradation cost, and compared Brest to another city, Brest, which is a medium weather city. By Brest here I mean the island, of course, and we have compared this to this degradation cost of the Western Island to another city, hot city, Dammam in Saudi Arabia. We can see that there is a huge impact. terms of constraint, as I mentioned later, we have different type of constraint, but in our case, important constraint should be the demand response, the power balance, and of course, depending on the type of network, here we have DC network, and this is specific to our case. But if we want to list main constraint, should be demand response, power balance, and of course, the grid connection. In our case, the island is not supposed to be connected to the main grid. These are some results to illustrate how it is easy to deploy an optimal EMS. So the first result about the load balance regarding a 6-hour shift period for this Western Island, and the second one is a result for the demand response, depending on 10% of demand response limit, 20%, 30%, so on, with different type of duration, 6, 10, and 23 hours. So we introduced here a huge demand response duration. So I would like also to highlight here that the deployed DC microgrids of the Western Island is including PV. We have two possibilities under study. Actually, we have one DC microgrid including, as you can see here, a tidal stream turbine. This tidal is actually deployed close to the island. We have wind turbine, onshore wind turbine. We have PV, and in terms of storage, we have two types of storage under study: classical batteries, lithium-ion batteries, and pumped hydro. And the proposed EMS here, we have proposed two-level optimization EMS, and that has been tested typically here in collaboration with the University of Aalborg. Okay, so this is how this EMS has been tested based on a hardware in the loop validation process. This is in the up figure here. This is the renewable energy power control loop, and down is the battery control loop. Okay, so now I will focus on some challenges and some prospects. The first one is the development of EMS strategies, but here typically at planning level.
Excuse me, Professor, can you hear me, please? We have to wrap up the session in 5 minutes. Can you please wrap up?
Yes.
Yeah, thank you.
Yes, sorry, I will finish in 5 minutes. Okay, thank you. Developing EMS strategy, but at planning level, which is not the case at this time. Another challenges is and prospect is to include additional functionality to the EMS. Here, I mean, one important thing is the power qualities. So we need to improve power quality, which is not the case at this time. Another challenges is the, as I mentioned here, is the weather forecast. This is important to reach a sort of optimal EMS. So this is actually and should be done using artificial intelligence. And another maybe challenge as a prospect is to consider, the microgrid systems by combining local and centralized EMS. I mean here to consider, a cluster of microgrids. As I mentioned, as it was seen in a previous slide, we need to consider the transactive energy concept, taking into consideration the privacy and local user and the economic benefits. And this can be done as it's shown here. We have already proposed a sort of direction, a sort of proposal of transactive power system as illustrated by this slide, typically for a microgrid approach. And I will finish my presentation by considering that we need to address for microgrid cyber security issues, typically cyber attacks, by the mean of the communication level. We have already tried to review the different type of cyber attack that can happen in a microgrid. So this is really a challenge for a microgrid, because the objective of cyber attacks is, of course, to block the energy and to disturb the energy, the power chain and the energy stability. And actually, to address this, the tendency regarding the literatures is to use machine learning. Machine learning seems to be the solution of choice to detect, identify, diagnose, and mitigate adversary attacks on the EMS. So sorry for the extra time, and this and my presentation, and thank you for your attention. I'm ready for the questions.
Thank you for your presentation, Professor Mohammed. It was really great to see your work, and I would invite all the participants if they have any questions.
Excuse me, I'm not hearing you well.
I have one question, Dr. Saab.
Oh, please.
You have given different methods of optimization of EMS. Which method you might be considering the best, because you are the expert of it, the best for the microgrids?
If I will understand thank you for your question, and if I will understand your question, so maybe you are asking for what in my opinion, what is the most efficient technique for EMS?
For EMS, yes, optimization, because there are some linear techniques and non-linear techniques in many things. Yes.
Okay, so if I come back to my presentation, I highlighted that actually, so this is my own opinion, maybe. My opinion is that is using machine learning, and typically reinforcement learning for both the optimal EMS, but also the chosen machine learning model you will adopt for the energy management optimization. You can use it also for other challenges I highlighted, typically the transactive energy and optimal transactive energy, and also to try to immune your microgrid against cyber attack. This is my opinion. Even if we are starting to use typically reinforcement learning, and we compare it to other classical method we already use, typically dynamic programming and MIP. We have also used meta heuristics, but seems that machine learning advantage is, of course, the computational burden. This is really maybe the main advantage, and the second main advantage is unique one methods for different objective: optimal EMS, transactive energy, and cyber threat detection and mitigation. I hope I answered the question.
Yeah, thank you. I have another question. How can you use reinforcement learning for, is it possible to use a multi-agent system to represent a microgrid with multiple entities?
Maybe the sound is not okay, but maybe can you repeat your question?
Yeah, my question is that if you talked about using reinforcement learning, I can understand it's very important. You can have multiple agents that are evolving in an environment that are reacting to the environment. My question is, have you ever considered using a multi-agent system to represent the optimization of a microgrid energy management system?
No, you mean here by microgrid cluster, yeah?
I mean, a multi-agent system where we can have, within a microgrid, we can have different sources that are represented by a single agent, and then they are working together in an environment to optimize. Have you considered this in your research
Yes.
center?
Yeah, yes. We have. I'm not time to come back to my side. Yes, we already use it. Yes.
Thank you.
Hi, Professor. I have a small question. Your presentation was very good and brief. I want your comment on some energy storage applications of hydrogen energy tanks, in which are currently under research, and many utilities are thinking to implement that for the energy storage instead of the batteries. So have you considered that in your research, and what you think the future prospect of hydrogen energy storage? Thank you.
Okay, yes. Thank you for your question. Yes, we actually, when I highlighted this, I come back to, I was talking about the Western Island. So we have two competing projects. So typically this one, we have typically two competing projects. We are proposing to use pumping hydro as a storage of course, for different reasons, for different advantages. Typically, the size, typically the lifetime of the systems, compared to another competing proposal from ADF company, which is proposing lithium-ion battery. So I think that battery is a really simple solution to deploy using lithium batteries, but typically this technology will, with the time, and typically in an island, suffer from the progressive aging issues and degradations compared to a pumped hydro systems. Typically here, the pumped hydro, the initial maybe drawback is the initial investment. But for an island, as I mentioned, in the Western Island, we have already an upper reservoir, and we need, of course, to connect the upper reservoir to the sea, considered here as the lower reservoir. So definitely, we are more on this side for this type of microgrid, of course, allowing to deploy a pumping hydro system. We have already tested for this. We are also proposed to introduce another type of storage, which is the air compression compressed air systems, which should be used close to the tidal stream turbine. But of course, here the investment costs, the capex are important. This is why actually we already worked on this pumped hydro, and we propose it. It has been adopted, but for cost issues, battery seems to be really a simple solution to adopt. But I'm still confident that pumped hydro is a solution of choice in terms, of course, of energy and size, of course.
Thank you, Professor.
Thank you, Professor. Thank you very much for joining us and for your interesting talk.
Thank you.
Thank you so much, sir, for your informative talk. We would like to request Dr. Kashif Imran to present the souvenir to Dr. Tahir Izhar. Now we would like to invite Dr. Kamran to present the shield to Dr. Kashif Imran. I will now announce break for lunch and prayers. The rest of the session will be resumed at 2 p.m.